What if everything you've ever experienced, every sunrise, every conversation, every moment of joy or sorrow, has already happened an infinite number of times before, and will happen again forever? We often think of time as a straight line, carrying us inexorably from birth to death, from past to future, never looking back. But what if that's not the whole story? What if time isn't a one-way arrow at all, but something far more mysterious, something that bends, twists, and even loops back on itself? This isn't just science fiction. It's a possibility that some of the most brilliant minds in physics are taking seriously today, and it challenges everything we thought we knew about reality, memory, and our very existence. In this video, we're going to explore the astonishing idea that time could be recycled, that the universe might not have a single beginning and end, but instead operates in endless cycles of birth, death, and rebirth. We'll dive into theories that suggest the flow of time we experience is just one part of a much larger, much weirder cosmic picture. From ancient philosophies that spoke of great cycles lasting billions of years to cutting-edge concepts in quantum mechanics and relativity, we'll journey through ideas that stretch the imagination to its limits. We'll look at how black holes might preserve information across eons, how the fabric of spacetime could contain hidden loops called closed timelike curves, and why some scientists believe that multiple universes with different arrows of time might be constantly springing into existence all around us. This is more than just a tour of abstract theories. It's an invitation to rethink your place in the cosmos. If time is looped, what does that mean for free will, for history, for the choices we make and the lives we lead? Together, we'll uncover secrets hidden in the cosmic microwave background, delve into the quantum puzzles that suggest time may be an illusion, and consider whether the universe itself might be a kind of perpetual motion machine, recycling not just matter and energy, but time itself. So join us on this journey. We're about to venture into one of the most profound and mind-expanding mysteries of all, the nature of time itself, and how it might not be what it seems. We take it for granted every single day. We remember yesterday, we plan for tomorrow, and we watch as moments slip from the future into the past, never to return. This one-way street of experience is so deeply ingrained in our lives that we call it the arrow of time. It's the reason you can't unscramble an egg, why you can remember the past but not the future, and why a cup of hot coffee left on the counter will eventually cool down to room temperature, never spontaneously reheating itself. This irreversible flow is one of the most fundamental features of our reality, and for over a century, physics has had a powerful explanation for it, the second law of thermodynamics. This law states that in any closed system, entropy, a measure of disorder or randomness, always increases. Think of it like a deck of cards. A new deck comes neatly ordered, but as soon as you shuffle it, it becomes disordered. It's incredibly unlikely that a random shuffle will ever return the deck to its pristine, factory order state. The universe is like that shuffled deck, constantly moving from a state of low entropy to high entropy, from order to disorder. This ever-increasing entropy gives time its direction, its arrow. This concept isn't just abstract, it defines the very story of our cosmos. The universe began in an incredibly ordered, low-entropy state, the hot, dense singularity of the Big Bang. From that moment, it has been expanding and cooling, with entropy steadily increasing. This expansion drives the formation of galaxies, stars, and planets. On a more personal level, it's the reason we are born young and grow old. Our bodies are complex, ordered systems that gradually break down, following the universe's relentless march toward disorder. Even our perception and memory are tied to this process. Our brains record memories because the formation of a memory is a process that increases entropy in the universe, making it irreversible. We can recall the past precisely because it was a state of lower entropy. The future, being a state of higher entropy, remains unknown and unrecorded. This arrow of time is so persuasive that it shapes not only physics but philosophy, influencing how we think about cause and effect, freedom and destiny. Yet for all its power, this view of time presents a profound puzzle. The fundamental laws of physics, whether Newton's mechanics, Einstein's relativity, or quantum theory, are almost entirely time-symmetric. They work just as well if time runs backwards. If you were to watch a film of two billiard balls colliding and ricocheting apart, the physics would look perfectly normal whether you played the film forwards or backwards. The equations don't care. But if you watched a film of a shattered vase reassembling itself and leaping back onto its pedestal, you would know instantly that it was being played in reverse. The microscopic laws are neutral, but the macroscopic world has a glaringly obvious direction. This disconnect is one of the deepest mysteries in science. How do time-symmetric laws give rise to a time-asymmetric world? The arrow of time, for all its feeling of absolute truth, might not be a fundamental property of the universe at all, but rather an emergent one, a feature of our specific circumstances within the cosmos. This realization is the crack in the door, the opening that allows us to consider truly radical possibilities. If our experience of time is contingent, a product of a particular arrangement of matter and energy, then what other arrangements are possible? Could time flow in a different direction elsewhere? Could it even curve back on itself? But what if the arrow of time isn't the final word? What if the universe itself is on a loop, an infinite cycle of creation and dissolution where time is not a one-way street but a circle? This idea, known as cyclic cosmology, is one of the oldest and most profound challenges to our linear view of time. Its roots stretch back millennia, far before modern physics, to the ancient spiritual traditions of India. In Hindu cosmology, time is not linear but cyclical, operating on a scale that is almost incomprehensible. The universe goes through repeated cycles of formation, existence, and dissolution, each one lasting for billions of years. A single cycle, known as a kalpa, is often compared to a single day in the life of the creator god Brahma. But even a kalpa is just a small part of a much grander cycle. These cosmologies describe a universe without a true beginning or end, only an endless, rhythmic dance of birth, death, and rebirth. Buddhist philosophy shares a similar view, teaching the concept of samsara, the endless cycle of rebirth that all beings are subject to until they achieve enlightenment. In these ancient worldviews, time is not a river flowing to a distant sea, it is a wheel forever turning. This ancient intuition finds a startling echo in one of the most ambitious theories of modern cosmology, proposed by the Nobel Prize-winning physicist Sir Roger Penrose. His model, called conformal cyclic cosmology, or CCC, suggests that our universe is just one in an endless sequence of universes, each one beginning with its own Big Bang and ending in its own heat death. But how can a new universe be born from the cold, empty, high-entropy ashes of an old one? The key lies in a process Penrose calls conformal rescaling. At the very end of time, when the universe has expanded to near nothingness and all matter has decayed or been swallowed by black holes, only low-energy photons and gravitational waves remain. In this vast, empty, and incredibly smooth state, the universe loses all sense of scale. Distances and durations become meaningless. A billion years and a single second are effectively the same. In this strange, scaled-down state, the end of one universe can be seamlessly connected to the beginning of another. The cold, empty end of our cosmos can be mathematically transformed or rescaled to become the hot, dense, low-entropy singularity of a new Big Bang. It's a breathtaking idea. The ultimate death of the universe is not an end, but a transformation, a reset button for reality itself. This process suggests something even more incredible, that time itself is being recycled. In Penrose's model, the arrow of time does not cease to exist, but it is, in a sense, rebooted with each new cycle. The low entropy beginning of our universe, which so puzzled physicists, is simply the conformally rescaled high entropy end of the previous eon, as Penrose calls each cycle. But if information is preserved in some form across these cycles, what does that mean for the contents of the universe? Penrose has even suggested that we might find evidence of a previous eon imprinted on our own. He and his colleagues have pointed to strange, concentric circular patterns found in the map of the cosmic microwave background radiation, the leftover heat from our own Big Bang. These anomalous circles, he proposes, could be the gravitational shock waves from colossal collisions between supermassive black holes in the universe that came before ours. If true, it would mean the cosmos has a memory. It would mean that the information of a past universe, its most dramatic events, are literally written in the sky, an echo of a time before time as we know it began. This idea of cyclic cosmology, both ancient and ultramodern, offers a radical vision, a universe without beginning or end, where time is not a line but a circle, forever renewing itself in an infinite loop of creation. Yet if the idea of a single, endlessly recycling cosmos feels vast, it is almost intimate compared to the next theory, which proposes that our entire universe is merely one tiny bubble in an infinite, frothing sea of cosmic foam. This is the breathtaking concept of eternal inflation, a theory that doesn't just give us one looped universe, but an infinite number of them, each potentially operating under its own unique set of physical laws, including its own peculiar arrow of time. To understand this, we need to rewind to the very first instance after the Big Bang. Most cosmologists agree that our universe underwent a period of incredibly rapid expansion known as inflation, a fraction of a second during which space itself expanded faster than the speed of light, smoothing out the cosmos and seeding the structures that would become galaxies. But what if that inflationary period never truly stopped? What if it's still happening right now in a realm beyond our perception? This is the core of eternal inflation. The theory suggests that the energy field that drove inflation, known as the inflaton field, does not switch off everywhere at once. Instead, it decays in localized patches, like bubbles spontaneously forming in a pot of boiling water. Each of these bubbles is a region where inflation has ended, and within that calm, stable region, a new universe is born, a pocket universe with its own Big Bang and its own subsequent evolution. Our entire observable cosmos is just one such bubble in an unimaginably vast multiverse. But outside our bubble, the inflationary expansion continues relentlessly, creating ever more space and spawning an infinite number of other bubble universes. This process is eternal, both into the future and possibly into the past, meaning the multiverse has no beginning and no end. It's a perpetual engine of creation, constantly giving birth to new realities. Now, here's where the concept of recycled time expands into truly uncharted territory. Each of these pocket universes, born from a quantum fluctuation in the inflaton field, can have wildly different properties. The fundamental constants of nature, the strength of gravity, the mass of an electron, the number of spatial dimensions, could be set randomly within each bubble. Some universes might be stillborn, collapsing instantly. Others might be vast, empty voids, and crucially for our journey, each one could have a completely different relationship with time. In some universes, the conditions might be just right for entropy to increase, creating a forward arrow of time identical to our own. But in others, the arrow might point backward, with universes moving from high entropy to low entropy. Inhabitants of such a universe would perceive time in reverse. They would remember the future and find the past unknown. Others still might have no predominant arrow of time at all, a chaotic jumble of cause and effect. This multiverse framework doesn't just allow for different directions of time, it demands them. This leads to an even more mind-bending possibility. Within this infinite ensemble of universes, some might naturally contain closed timelike curves, those loops in space-time we touched on earlier, as a fundamental feature of their structure. A universe with a certain geometry or with exotic matter could have regions where time curves back on itself, not as a rare anomaly but as a common part of its landscape. In such a universe, time wouldn't just be linear with a set direction, it would be inherently recyclable. An event could be both the cause and the effect of itself, and history could literally repeat in a tight, local loop. This means that the recycling of time isn't confined to a single, grand cosmic cycle like Penrose's. Instead, it could be happening in countless ways across countless universes. Some universes might be entirely looped, while others might contain isolated time machines within an otherwise linear flow. The multiverse becomes a canvas of temporal possibilities, where time is recycled not on a single grand scale, but on an infinite variety of scales from the microscopic to the cosmic. It suggests that our own experience of a straightforward, irreversible timeline is not the rule, but merely one unique possibility in a much richer and more complex meta-reality. While the idea of entire universes cycling or a multiverse bubbling with alternate timelines is staggering in its scale, the next theory brings the possibility of recycled time much closer to home, or at least to the familiar territory of Einstein's general relativity. This theory doesn't require the death and rebirth of a cosmos. Instead, it suggests that the very fabric of spacetime could be twisted into a loop right here in our own universe, creating what physicists call a closed time-like curve. Imagine setting out on a journey through space, following a path that seems perfectly normal, only to discover that your trajectory has somehow brought you back to the exact same point in space, but at a time before you even left. You wouldn't just be traveling to a distant star, you'd be traveling into your own past. This isn't a magic trick or a fantasy. It's a rigorous mathematical prediction of Einstein's equations, a solution that allows for the fabric of reality to be stitched together in a way that makes time travel a theoretical possibility. The first person to discover such a solution was the legendary logician and mathematician Kurt Gödel, a close friend of Einstein's. In 1949, Gödel presented a model of a universe that was rotating, much like a vast cosmic whirlpool. In this spinning cosmos, Gödel showed that if you had a rocket ship powerful enough, you could literally fly a path that would bring you back to your own past. This path is the closed time-like curve. In our everyday experience, timelines are open. They stretch from the past into the future without connecting. But in Gödel's rotating universe, timelines can become closed loops, circles in the four-dimensional fabric of spacetime. Gödel himself was deeply troubled by this implication, as it seemed to undermine any objective notion of past, present, and future. If you can visit your own past, then the past is just as real and accessible as a distant location, challenging the very foundation of how we experience reality. Another, perhaps more famous, proposal for a time machine comes from the concept of a wormhole, often called an Einstein-Rosen bridge. A wormhole is a hypothetical tunnel, a shortcut connecting two distant points in spacetime. According to general relativity, such a structure could exist. Now, if one end of this wormhole were to be taken on a journey at a significant fraction of the speed of light, or placed near an incredibly strong gravitational field like a black hole, time would pass more slowly for that end due to the effects of time dilation. Meanwhile, the other end of the wormhole, left behind in a less extreme environment, would age normally. After a while, you would have a tunnel connecting not just two places but two different times. Walking through one end would bring you out the other, not just somewhere else but sometime else. If the exit point was in your own past, you would have created a stable, traversable closed timelike curve. You could, in theory, step through and shake hands with your younger self. Of course, this incredible possibility comes with a host of infamous paradoxes, the most famous being the grandfather paradox. What if you were to travel back in time and prevent your own grandfather from meeting your grandmother, thereby preventing your own birth? If you were never born, you could never have traveled back in time to commit the act, creating a logical inconsistency that seems to make the entire idea impossible. These paradoxes strike at the heart of causality, the principle that cause must precede effect. If closed time-like curves exist, they threaten to unravel the logical consistency of the universe, allowing effects to create their own causes or even negate them entirely. Some physicists argue that the laws of quantum mechanics might somehow conspire to prevent such paradoxes, perhaps through a mechanism that ensures only self-consistent events can occur within a loop. Others suggest that the very act of trying to create a paradox would require infinite energy or be stopped by some as yet unknown physical law, a kind of cosmic censorship protecting the timeline. But let's set aside the paradoxes for a moment and consider the profound implication for recycled time. A closed time-like curve is the ultimate recycler. Within that localized loop of space-time, a finite amount of time is endlessly repeated. Every event, every particle, every bit of information that enters the loop is destined to live out the same sequence of events over and over again forever. It's a pocket of eternity within the larger flow of linear time. For an observer outside the loop, history might proceed normally, but for anything caught inside, time is not an arrow but a circle, a perfect and unbreakable cycle where the end is forever tied to the beginning. This isn't a grand cosmic cycle spanning billions of years. It's a personal, intimate loop where time itself is recycled on a human scale, offering a terrifying and fascinating glimpse into a reality where history is not a record of what was, but a stage that can be revisited and potentially rewritten. Yet for all the grandeur of rotating universes and cosmic wormholes, the most profound challenge to our everyday experience of time might not be hidden in the vastness of space, but in the bizarre and counterintuitive world of the very small. When we descend into the quantum realm, the familiar ticking clock of our macroscopic world begins to dissolve, revealing a domain where time itself behaves in a radically different way. At the heart of quantum mechanics lies a deep and fundamental symmetry. The laws that govern particles are, for the most part, completely reversible. If you were to make a film of two electrons colliding and scattering off one another, and then play that film backwards, you would be utterly unable to tell which version was the original. The mathematics describing their interaction works perfectly in both temporal directions. This stands in stark contrast to the irreversible, entropy-driven arrow of time that defines our daily lives. It presents a fascinating puzzle. How does a universe built on time-symmetric microscopic rules give rise to the overwhelming time asymmetry we see all around us? This disconnect hints at a revolutionary idea that the flow of time might not be a fundamental feature of the universe at all, but rather an emergent property, a collective illusion that arises from the complex interactions of countless particles. One of the most compelling proposals in this direction comes from the work of physicists John Wheeler and Bryce DeWitt. In the 1960s, they attempted to combine the principles of quantum mechanics with general relativity, a crucial step toward a theory of quantum gravity. The result was the Wheeler-DeWitt equation, a profound and controversial formulation that describes the quantum state of the entire universe. But this equation has a startling property: the variable for time completely disappears from it. It suggests that at the most fundamental level, the universe is static and timeless. There is no past or future baked into the core laws. There is only a vast, frozen landscape of possible states, often called the block universe. In this view, what we perceive as the flow of time is akin to a movie that already exists in its entirety on a DVD. Our consciousness simply plays it out, frame by frame, creating the illusion of movement and change. If time is not fundamental but emergent, this opens up extraordinary possibilities for how it might be manipulated, looped, or recycled. The quantum realm is already filled with phenomena that defy classical intuition, such as superposition, where a particle exists in multiple states at once until it is observed. Could time also exist in a kind of superposition? Some interpretations of quantum mechanics, like the transactional interpretation, even allow for influences that travel backwards in time. In this model, a particle in the present can send a signal both forward and backward in time, and reality is shaped by a handshake between the past and the future. This introduces a form of retrocausality, where effects can precede their causes on a quantum level. While this doesn't create a macroscopic time machine you could step into, it suggests that the fabric of causality at the universe's foundation might be far more flexible and loopy than we ever imagined, with tiny threads of influence constantly weaving a tapestry that connects what was, what is, and what will be. This quantum perspective fundamentally reshapes our search for recycled time. We are no longer just looking for massive cosmic structures like rotating universes or wormholes. We are now considering the possibility that time loops could be a fundamental feature of reality at the quantum scale, woven into the very laws of physics. The quest to unify quantum mechanics and gravity, the holy grail of modern physics, might ultimately reveal a reality where time can be knotted, braided, or even stitched into closed loops through purely quantum processes. In such a universe, recycling wouldn't be a rare cosmological event, but a constant, humming background process, with information and influence cycling through time in ways that are invisible to us but essential to the structure of everything. But if the quantum world suggests time might be an emergent illusion, there is another cosmic phenomenon where the nature of time and information becomes not just theoretical, but a matter of life and death for the fundamental laws of physics, the black hole. These enigmatic objects where gravity becomes so intense that not even light can escape are not just destroyers of matter. They may also be the universe's ultimate recyclers, holding the key to understanding how information, and perhaps time itself, could be preserved across cosmic cycles. To see how, we must confront one of the most famous puzzles in modern physics, the black hole information paradox. The story begins in the 1970s with a seminal discovery by physicist Stephen Hawking. He realized that due to quantum effects near the event horizon, the point of no return black holes are not completely black. They slowly leak radiation, a faint glow of particles now known as Hawking radiation. This process causes the black hole to gradually lose mass and, over astronomical timescales, completely evaporate, vanishing from the universe. This created a catastrophic problem. According to the fundamental principles of quantum mechanics, information cannot be destroyed. information, in this context, means the specific quantum state of every particle that fell into the black hole, its mass, its spin, its type. The theory states that if you had a perfect, impossibly powerful computer, you could theoretically take the final state of a system and run the laws of physics backwards to reconstruct its entire history. But Hawking's calculations suggested that the radiation leaking out was completely random, bearing no fingerprint, no imprint, no connection whatsoever to the information of the matter that had formed the black hole. When the black hole finally evaporates, that information is seemingly erased from existence, a direct violation of a cornerstone of quantum theory. It was as if you burned a book and the smoke that rose up contained not a single letter of the original text, just featureless, random ash. This is the information paradox. Does the black hole truly destroy information, forcing us to rewrite quantum mechanics, or is our understanding incomplete? The potential solution to this paradox is where the concept of recycling takes a spectacular leap forward. What if the information isn't destroyed at all? What if it is preserved but in a way we are only beginning to understand? One compelling idea is black hole complementarity, a principle proposed by physicists Leonard Susskind and others. It suggests that from the perspective of an outside observer, the information of anything falling into a black hole is not lost behind the event horizon. Instead, it is scrambled and encoded onto the event horizon itself, a two-dimensional surface, through a process related to its increasing temperature and entropy. The event horizon acts like a chaotic, cosmic hard drive, storing the quantum information of everything that has ever fallen in. Then, as the black hole radiates via Hawking radiation, this information is slowly and carefully emitted back out into the universe, woven into the fabric of the radiation itself. For an outside observer, the information is never lost. It is just incredibly difficult to decode from the random-seeming Hawking radiation. This means the black hole isn't a terminal garbage disposal. It's a transformer, a processor that takes in complex matter and energy and eventually returns its fundamental information to the cosmos, ready to be used again. This leads us to an even more profound concept, the holographic principle. If all the information about a three-dimensional volume of space, everything inside the black hole, can be encoded on its two-dimensional boundary, the event horizon, could this be a general property of the universe? The holographic principle boldly suggests that yes, our entire three-dimensional reality, with all its rich depth and volume, might actually be a projection from a two-dimensional surface of information at the cosmic horizon. We are, in a sense, living inside a cosmic hologram. This radically changes our view of black holes. They are not just oddities, they are the simplest places to see this holographic nature of reality at work. The information that falls in doesn't cease to exist. It is painted onto the surface, preserved for eternity. Now connect this back to our larger theme of recycled time, and the implications are staggering. If information is never truly destroyed, only transformed and stored, then it is always available to be used again. In a cyclic cosmology like Penrose's conformal cyclic cosmology, the information encoded on the event horizons of supermassive black holes from a previous universe could be the very seeds from which the next universe forms. The cosmic memory is not lost. The data of entire civilizations, of stars and planets, of every event that ever happened, could be imprinted onto the fabric of spacetime itself, waiting to be unfolded again in a new cosmic cycle. The black hole, once thought to be the ultimate end of time and information, may in fact be its greatest librarian, a cosmic archive ensuring that the story of the universe is never forgotten, but endlessly checked out, read, and returned for the next iteration of reality. But if the arrow of time is so deeply tied to the relentless rise of entropy, what would happen if, against all odds, that trend were to suddenly reverse? We've established that the universe is like a clock slowly winding down, moving from order to disorder. But what if, in some forgotten corner of the cosmos, the clock began to wind itself back up? This isn't just a thought experiment. It's a possibility that emerges directly from the statistical nature of the laws of thermodynamics themselves. To understand how, we need to journey back to the late 19th century and the work of Ludwig Boltzmann, the physicist who first connected entropy to the microscopic world of atoms and probability. His insights not only gave us a deeper understanding of the arrow of time, but also opened the door to one of the most bizarre and fascinating ideas in all of physics, that our entire experienced reality, from the Big Bang to this very moment, might be nothing more than a random, temporary blip in an otherwise chaotic and timeless void. Boltzmann's great revelation was that entropy is not a fundamental force pushing the universe toward disorder. It is simply a matter of overwhelming probability. Think of it like this: there is only one way for a room to be perfectly neat and ordered, but a nearly infinite number of ways for it to be messy. If atoms are moving around randomly, they are vastly more likely to stumble into one of the countless messy states than to arrange themselves into the single, specific ordered one. The increase of entropy is just the universe taking the path of least resistance, moving toward the more probable configurations. But, and this is the crucial twist, probability is not certainty. In a system where particles are moving randomly, there is always a chance, however astronomically small, that they will randomly arrange themselves into a highly ordered state. It is incredibly unlikely that all the air molecules in a room will suddenly rush into one corner, leaving you gasping in a vacuum, but the laws of physics do not strictly forbid it. The probability is just so vanishingly small that you could wait longer than the current age of the universe and never expect to see it happen. This line of thinking led Boltzmann to a truly radical hypothesis. If our universe began in a state of maximum entropy, a featureless, high-entropy soup of particles in perfect equilibrium, it would be a state of no change, no structure, and no arrow of time. It would be a timeless, dead void, but within this eternal equilibrium, random quantum fluctuations would still occur. Once in an incomprehensibly long while, a fluctuation would be large enough to create a massive, spontaneous drop in entropy, forming a pocket of order within the surrounding chaos. Boltzmann proposed that our entire observable universe might be just such a rare fluctuation. In this view, the low-entropy Big Bang wasn't a special beginning, it was a statistical accident. We find ourselves in this bubble of order not because it's the norm, but simply because conscious observers like us can only exist in such rare, ordered regions where complex structures like planets and brains can form. Now take this staggering idea one step further. If our universe is one such fluctuation, why couldn't there be others? And within those other fluctuations, the statistical drop in entropy might not play out exactly as it did in ours. This is where the possibility of time reversal emerges from the realm of pure mathematics into a conceivable, if unlikely, physical scenario. Imagine another universe-sized fluctuation where the initial conditions cause entropy to decrease as the fluctuation evolves rather than increase. For conscious beings inside that bubble, their experience of time would be the exact opposite of our own. They would perceive a universe that becomes more ordered as they move forward in their personal time. They would see shattered vases reassemble on tables, waves retreat back into the ocean, and people growing younger instead of older. Their arrow of time would be pointed backward relative to ours. They would remember what we would call the future and anticipate what we would call the past. This leads to the mind-bending possibility of local temporal loops. In the vast equilibrium void, an infinite number of these entropy fluctuations could pop in and out of existence. Most would be small and short-lived. But some might be structured in such a way that their evolution forms a closed loop. A fluctuation could appear, decrease in entropy to a minimum point, and then increase again, returning to the high entropy equilibrium from which it came. For any sentient beings within that bubble, their entire history would be a closed circle. They would experience time flowing in one direction until they reached the point of minimum entropy, what they might perceive as the end of their universe, only to find that the flow of time itself seems to reverse, carrying them back along their own history toward their beginning. They would be living in a recycled time loop, not on a cosmic scale dictated by gravity, but on a statistical one dictated by pure chance. Their universe would have no true beginning or end, only an eternal recurrence driven by the random dice roll of atomic motion, a pocket of recycled time existing within a timeless entropic sea. But what if the smooth, continuous fabric of spacetime we take for granted is actually an illusion, a kind of mirage emerging from a much more fundamental and granular reality? This is the provocative premise of causal set theory, an approach to quantum gravity that suggests the universe is not a seamless continuum, but is instead built from a vast collection of discrete, indivisible units of spacetime. Imagine the universe not as a flowing river, but as a colossal, cosmic pointillist painting. Up close, you would see individual dots, but from a distance, they blend together to create the illusion of a smooth, continuous image. In causal set theory, these dots are the fundamental building blocks of reality, finite, elemental events. The theory gets its name from two key features. These elements form a set, a mathematical collection of distinct objects, and they are connected by causal relationships, meaning each event can influence or be influenced by others. This creates a vast, shimmering network of cause and effect, a cosmic web where the relationship between events is more fundamental than the concepts of space or time themselves. In this framework, the familiar notions of distance and duration are not primary. You can't measure the space between two fundamental events with a ruler, nor the time between them with a clock. Instead, everything is defined by their causal order, which event can affect which other event. This perspective turns our conventional understanding on its head. In Einstein's relativity, spacetime is a dynamic, continuous stage on which particles perform. But in causal set theory, the stage itself is built from the relationships between the actors. The smooth, four-dimensional universe of our experience emerges from the collective, statistical behavior of a near-infinite number of these discrete causal links. Much like the smoothness of a material like metal emerges from the chaotic jostling of its individual atoms. This discrete foundation provides a completely new way to think about one of the most perplexing problems in physics: how to reconcile the smooth geometry of general relativity with the granular quantum nature of the subatomic world. This discrete structure offers a remarkably elegant and paradox-free way to conceptualize looped time. In a continuous spacetime, a closed timelike curve is a smooth, mathematical loop that can lead to infamous logical nightmares like the grandfather paradox. But in a causal set, time isn't a line, it's a network of connections. A causal loop would simply be a closed chain of influence within this network. Picture it not as a circle drawn on a page, but as a loop in a chainmail shirt. One event influences the next, which influences the next, and so on, until the chain of causation eventually circles back to influence the very first event in the sequence. Because the theory is fundamentally discrete, this doesn't create the same kind of logical inconsistency. The loop is a fixed, unchanging structure within the greater network. There's no first event in the loop to create a paradox, all events are simply linked together in a cycle of mutual causation. An observer within such a loop would experience time as cyclical and repetitive, living the same sequence of events over and over, but the overall physics of the causal set remains perfectly consistent and well-defined. The discrete nature of reality provides a built-in regulator, preventing the infinite regress and contradictions that plague continuous models of time travel. The implications of this for quantum gravity are profound. Many physicists believe that a successful theory of quantum gravity must somehow resolve the singularities predicted by general relativity, those points of infinite density at the heart of black holes and at the beginning of the Big Bang. In a continuous spacetime, these infinities are a sign that the theory has broken down. But if spacetime is discrete, there is a natural limit to how small things can get. You cannot have infinite density because you cannot pack matter into a volume smaller than a single, fundamental spacetime atom. This discretization effectively replaces the troubling singularity with an extremely dense but finite state. This opens the door to models of the universe that might bounce rather than bang. Instead of a singularity marking the absolute beginning of time, a previous universe could have collapsed to a state of maximum density before rebounding into a new expansion phase, with the causal links from the old cycle providing the seeds for the new one. In this view, time isn't created or destroyed at a singularity. It is recycled through a discrete transition, with the causal network reconfiguring itself into a new order. Causal set theory, therefore, doesn't just allow for recycled time as a curious possibility. It provides a robust, logical, and paradox-free foundation for it, suggesting that the endless renewal of the cosmos could be an inherent feature of a universe built from discrete causal connections. So if the universe's arrow of time is not a fundamental rule but a statistical fluke, a rare bubble of order in a sea of chaos, we are immediately faced with a deeply personal question. Why does our particular bubble have the specific properties that it does? Why do we experience a consistent flow from past to future and not some other arrangement? This line of inquiry leads us directly to one of the most fascinating and sometimes controversial concepts in modern cosmology, the anthropic principle. In its simplest form, the anthropic principle suggests that the observed properties of our universe must be compatible with the existence of observers who are here to observe them. We should not be surprised to find ourselves in a universe that has the right conditions for life, because in a universe that didn't, we simply wouldn't be around to wonder about it. It sounds almost trivial, like a tautology, but when applied to the vast ensemble of possibilities suggested by theories like eternal inflation, it becomes a powerful tool for explaining why our local reality looks the way it does, including the very nature of time itself. Consider the multiverse, that frothing ocean of bubble universes we discussed earlier, each with its own randomly selected physical laws and constants. In this infinite variety, the direction of time is just another variable. Some universes might have a strong, consistent arrow of time like our own. Others might have a weak arrow where entropy increases so slowly that complex structures never form. Some might have no predominant arrow at all, existing in a timeless, chaotic equilibrium. And still others might have a reversed arrow where what we call the Big Bang is actually their big crunch, and their entire history runs backwards from our perspective. Now ask yourself, in which of these universes could conscious, intelligent life evolve? The answer is almost certainly only in those with a strong and consistent arrow of time. The formation of stars, planets, and ultimately living organisms requires processes that are fundamentally irreversible. A star, for instance, is a giant engine that burns fuel, converting lighter elements into heavier ones and radiating energy out into space. This process increases entropy and defines a clear direction in time. In a universe without a reliable arrow of time, where cause and effect are constantly flipping, such long, stable, complex chains of events would be impossible. Planets couldn't form stable orbits around stars. Chemical reactions couldn't proceed predictably to build complex molecules, and neurons in a brain couldn't fire in a sequence that allows for thought and memory. Consciousness, as we understand it, seems to require a stable timeline. This means we should not be surprised that we find ourselves in a universe with a past-to-future flow. It is not that this direction is special or mandated by a deeper law. It is simply the only type of universe where beings like us can arise to take note of it. The anthropic principle acts as a cosmic selection effect. We are not seeing a representative sample of all universes. We are seeing the one slice of reality that is hospitable to our form of life. This perspective completely reframes the mystery of the arrow of time. The question is no longer, why does time have a direction? But rather, given that we exist, the direction of time in our region must be such that we can exist. The low entropy beginning of our universe, which seems so incredibly improbable, becomes a necessary precondition for our own existence, not a bizarre accident in need of a unique explanation. This line of thinking opens up a breathtaking possibility that universes with recycled or looped time could be incredibly common in the multiverse, but they would be barren, empty, and silent. They could be filled with fascinating physics regions where time forms perfect closed circles, or where entropy fluctuates wildly, but they would be devoid of any observers to witness these wonders. A universe with a tightly looped timeline, for instance, might reset itself every few million years. While such a universe could theoretically exist, any complex structures that began to form would be periodically wiped clean, reset back to a primordial state before sentience could ever emerge. These universes would be cosmic ghost towns, their intricate temporal mechanics playing out to an empty audience. Our own universe, with its relentless and linear march toward higher entropy, might seem dull by comparison, but it is this very dullness, this stability and predictability, that provides the long, uninterrupted runway necessary for life to accelerate into existence. The arrow of time, therefore, might be less a law of physics and more a requirement of biology, a necessary feature of any universe that contains beings capable of asking why it has that feature in the first place. This journey into the nature of time has taken us from the colossal scales of cyclic universes down to the granular building blocks of reality itself. But to truly grasp how a one-way arrow could emerge in the first place, we must venture into the world of the infinitesimally small, to the realm of particle physics, where some of the most profound secrets of time's origin are hidden. Here we encounter a powerful and elegant concept that shapes everything from the forces that bind atoms to the very structure of the cosmos: symmetry. In physics, a symmetry exists when a situation remains unchanged under a specific transformation. Rotate a perfect sphere and it looks the same. That's symmetry. The fundamental laws of physics are rich with these beautiful symmetries. For a long time, physicists believed these symmetries were perfect and unbreakable. But then they made a startling discovery. The universe in its present state is fundamentally lopsided. The perfect symmetries of the laws are hidden, broken by the world we actually see around us. This concept of broken symmetry may hold the key to understanding the greatest asymmetry of all, the arrow of time. To see how this works, imagine a pencil balanced perfectly on its sharpened tip. This setup is highly symmetric. It looks the same from every direction, but this state is also incredibly unstable. The slightest vibration, the faintest breath of air, will cause it to topple over and fall onto its side. In doing so, it picks a specific direction to fall. It breaks the symmetry. The underlying law of gravity is still perfectly symmetric. It doesn't favor one direction over another, but the final outcome is undeniably asymmetric. The universe may have begun in a similar state, a perfectly symmetric, high-energy state where all forces were unified and all directions were equal. But as it expanded and cooled, it underwent a series of cosmic phase transitions, much like steam condensing into water or water freezing into ice. At each critical juncture, the universe had to choose a state, toppling over like that pencil and breaking a fundamental symmetry in the process. It is this cascade of broken symmetries that may have given rise to the four distinct forces we see today, and most importantly, laid the foundation for time's irreversible arrow. One of the most crucial and dramatic of these symmetry-breaking events concerns the very stuff we are made of, matter. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. For every particle of matter produced, a mirror image particle of antimatter should have been created alongside it. And since matter and antimatter annihilate each other on contact in a burst of pure energy, this cosmic confrontation should have left behind a universe containing nothing but light, a vast, empty sea of radiation with no stars, no planets, and no us. Clearly, that is not what happened. Our universe is overwhelmingly made of matter. Something must have happened in those first fleeting moments to break the perfect symmetry between matter and antimatter, allowing a tiny, 1 in a billion advantage for matter to survive the great annihilation. That something is a phenomenon known as CP violation. CP violation is a subtle but profound effect discovered in the behavior of certain exotic particles called kaons and B mesons. The C stands for charge conjugation, which means swapping a particle for its antiparticle. The P stands for parity, which is like looking at the universe in a mirror. For a long time, physicists believed the laws of physics were symmetric under this combined CP operation. A reaction involving particles should look identical to the mirror image reaction involving antiparticles. But experiments showed this wasn't always true. In extremely rare decays, these particles revealed a tiny preference, a slight bias in the way they broke down that treated matter and antimatter differently. This minuscule breaking of CP symmetry is the only known process in all of physics that provides a mechanism to distinguish between the past and the future on a fundamental level. It offers a physical reason why time might have a preferred direction. This tiny crack in nature's mirror is the reason we exist. It's the reason any complex structure exists at all. And it is intricately linked to the arrow of time through a deep and beautiful connection proposed by the physicist John Bell, known as the CPT theorem. This theorem states that any quantum field theory that is relativistic must be symmetric under the combined operation of C swapping particles and antiparticles, P mirror reflection, and T time reversal. This is considered an absolute, unbreakable symmetry of nature. Because we have observed that CP symmetry is violated, the T symmetry, the symmetry of time reversal, must also be violated to keep the overall CPT symmetry intact. In other words, the same physical process that allowed matter to dominate over antimatter also dictates that the laws of physics must treat the forward direction of time differently from the backward direction. The origin of matter and the arrow of time are two sides of the same coin, both arising from the same fundamental broken symmetry in the early universe. The cosmic preference for matter over antimatter is inextricably woven into the fabric of time's one-way flow. This profound link forces us to reconsider what it would mean to truly reverse or recycle time. If we could somehow win the universe backwards, we wouldn't just see eggs unscramble and people grow younger. we would see the very laws of particle physics themselves operating in reverse. The subtle processes of CP violation would run in the opposite direction, and antimatter would begin to dominate over matter. A universe with a reversed arrow of time would, by necessity, be a universe made mostly of antimatter. This leads to a fascinating and testable idea. If our universe is part of a larger multiverse or a cyclic cosmos, there might be other universes or other regions of our own universe where the arrow of time points backward relative to ours. From our perspective, such a region would be made of antimatter and its history would be running in reverse. For observers in that region, of course, they would perceive their time as moving forward and would see us as the antimatter universe with the reversed timeline. The broken symmetry that defines our local arrow of time might not be universal. It could be just one possibility, a path chosen at the birth of our cosmic domain, with other domains having made a different choice, leading to a different flow of time and a different dominant type of matter. Therefore, the possibility of recycled time in a grand, cyclic model would require more than just a gravitational bounce or a quantum reset. It might necessitate the restoration of these broken symmetries. At the moment of maximum contraction or at the conformal boundary between cycles, the extreme energy and density might wipe the slate clean, restoring the perfect, symmetric state of the early universe. The pencil stands upright once more. Then, as the new cycle begins and the universe expands and cools again, it undergoes its phase transitions anew, breaking its symmetries once more. It could fall in the same direction, recreating an arrow of time identical to the previous cycle, or it could fall in a different direction, creating a universe with a reversed arrow of time or even with different fundamental constants. The recycling of time is not just a rewinding of the cosmic clock. It is a reprocessing of the very foundations of physics, a renewed breaking of symmetry that gives birth to a new timeline, a new direction, and a new reality from the ashes of the old. While the idea of broken symmetries paints a vivid picture of how time's arrow might have been forged in the fires of the early universe, it still operates within a framework that assumes a singular beginning, a definitive starting point from which everything unfolds. But what if that very assumption is wrong? What if the Big Bang was not a true beginning, but merely a transition, a moment of cosmic rebound from a previous state of existence? This is the extraordinary promise of loop quantum gravity, a leading approach to unifying general relativity and quantum mechanics that offers a breathtakingly different vision of cosmic origins, one where the universe is eternal and time is endlessly recycled through a series of great bounces. To appreciate this radical departure from the standard model, we must first confront the problem it aims to solve, the singularity. In Einstein's theory of general relativity, the Big Bang is described as a point of infinite density and temperature where the known laws of physics simply break down. It is the ultimate barrier, a place where space and time cease to have any meaning. For decades, physicists have sought a theory of quantum gravity to smooth out this infinity, to describe what really happened at time zero. Loop quantum gravity, or LQG, does this by reimagining the very fabric of spacetime. Instead of a smooth, continuous continuum, LQG proposes that space is woven from tiny, indivisible loops, one-dimensional threads of gravitational field. Think of it as the universe's underlying fabric being a kind of network, a spin network where these loops intersect at nodes. The area of a surface or the volume of a space isn't continuous. It comes in discrete, tiny Planck-sized units, much like a digital image is made of individual pixels. This granularity of space provides a natural cutoff that prevents the infinite densities predicted by classical relativity. This discrete structure leads to a stunning revision of cosmic history. In the standard Big Bang model, if you rewind the clock, the universe gets hotter, denser, and smaller until it converges on that impossible singularity. But in the LQG model, as you rewind towards what we call the Big Bang, the quantum nature of geometry becomes dominant. The density and curvature reach a tremendous maximum, but instead of soaring to infinity, they are stopped in their tracks by the fundamental graininess of space. The repulsive force generated by this quantum geometry becomes so powerful that it overwhelms the attractive force of gravity. The collapse of a previous universe halts and reverses course. The Big Bang is replaced by a big bounce. The universe does not emerge from a singularity. It re-emerges from a supremely dense quantum phase, a cosmic springboard that launches a new epoch of expansion. In this view, our universe is not the first and only chapter. It is merely the latest in an endless series of expansions and contractions, a cosmic heartbeat echoing through eternity. This has profound implications for the arrow of time and the concept of recycled history. In each cycle, the universe collapses to an incredibly hot, dense, and chaotic state at the bounce. This state effectively acts as a cosmic blender, scrambling all the information and structure that had accumulated in the previous cycle. The extreme conditions would wipe the slate almost clean, resetting the thermodynamic clock. As the new universe bursts forth from the bounce and begins its expansion, it starts anew with a low entropy state, re-establishing a clear arrow of time pointing from this new beginning toward a future of increasing disorder. The cycle of time itself is recycled. Each bounce represents both an end and a beginning, the death of one cosmic era and the birth of the next, complete with its own new arrow of time. It's a vision of cosmic renewal far more direct and physical than the abstract conformal rescaling of Penrose's model. Here, the universe is literally reborn from its own collapsed remains. But if each bounce scrambles everything, does that mean the universe has no memory? Is each cycle completely isolated, with no connection to what came before? The answer might be more nuanced. While the intense conditions of the bounce would erase most macroscopic information, stars, galaxies, and civilizations would be utterly obliterated. Some fundamental quantum information might persist. The quantum state of the universe at the end of one contraction could potentially influence the quantum state at the beginning of the next expansion. This is a bit like taking a complex computer program, compressing it into an encrypted file, and then using that file as the seed to generate a new, seemingly different program. The output looks entirely novel, but it was deterministically generated from the compressed data of the old one. In this way, some faint echo of a previous universe might be imprinted onto the new one. This isn't about preserving specific events or structures, but rather a more abstract quantum-level inheritance. The new universe wouldn't contain the ruins of old galaxies, but its fundamental constants, its particle content, or even the very laws of physics themselves might be determined by the quantum state of the universe that came before it. Each cycle would not be an exact replica, but it wouldn't be entirely random either. There could be a deep, hidden connection woven into the quantum fabric of reality, a subtle thread of causality linking each great bounce to the next, ensuring that the story of the cosmos, though periodically rewritten, is never truly started from scratch. Yet for all its grandeur, loop quantum gravity still operates within the familiar confines of 3 dimensions of space and 1 of time. But what if our entire universe is just a tiny slice of a much larger, higher-dimensional reality, and the recycling of time is not a property of our universe alone, but a consequence of its motion within this grander cosmos? This is the astonishing promise of string theory. a framework that not only suggests the existence of extra dimensions, but uses them to weave a cosmic narrative where time loops are not just possible, but an integral part of the engine of creation itself. To grasp this, we need to step beyond the point-like particles of traditional physics and into a world where the fundamental constituents of reality are unimaginably tiny, vibrating loops of energy strings. The different vibrational patterns of these strings give rise to every particle and force we see, from electrons to photons to gravity. But for the mathematics of string theory to work consistently, it requires something extraordinary. The universe must have more than the 3 spatial dimensions we experience. It needs 10 or even 26 dimensions, all curled up into a space so small we cannot perceive them. This idea of hidden dimensions might sound like pure abstraction, but it leads directly to one of the most visually compelling models for a cyclic universe, brain-world cosmology. In this picture, our entire 3-dimensional universe is not floating isolated in a void. Instead, it is a 3-dimensional brane, short for membrane, existing within a higher dimensional space called the bulk. Think of our universe as a single, infinitely large slice of bread within a cosmic loaf. But here's the revolutionary part. There could be other branes, other slices, parallel to ours in this higher dimensional bulk. These other universes could be mere millimeters away from us in an extra dimension we cannot see or access directly, each with its own particles, forces, and laws of physics. Our entire reality is confined to our brain. Everything we see and feel is stuck to it, like images projected onto a screen. Only gravity, in some models, is able to leak out into the bulk, which could explain why it is so weak compared to the other fundamental forces. This setup provides the stage for an incredible mechanism to recycle time, the cyclic model of colliding branes, proposed by physicists Paul Steinhardt and Neil Turok. This theory suggests that the Big Bang was not a singular point of creation, but a catastrophic, yet controlled, collision between our 3-dimensional brane and another parallel brane moving through the higher dimensional bulk. Imagine 2 enormous, perfectly flat sheets floating silently toward each other in a vast, dark space. As they draw closer, the attractive force between them grows stronger. They eventually collide with tremendous energy, but then simply bounce apart. From our perspective, trapped on our brain, that collision would appear as an event of unimaginable energy and density, a hot, dense state that looks exactly like the traditional Big Bang, seeding the formation of galaxies and stars. After the collision, the branes fly apart, and our universe enters its phase of expansion and cooling. But the gravitational attraction between the branes eventually halts their separation and pulls them back together again, setting the stage for another collision, another Big Bang, another new beginning. In this breathtaking vision, time is recycled on a scale that dwarfs all previous models. Each cycle begins with a bang, a collision, and ends as the branes move apart, only to be drawn together once more. The arrow of time in our universe is reset with each new collision. The incredible heat and order generated by the impact provides the low entropy starting point for a new cosmic epoch. This model elegantly avoids the problem of a singularity. The branes are simply moving and colliding in a smooth, higher dimensional space. There is no point of infinite density, no breakdown of physics. The universe, or rather, the multibrane system, could be eternal, with an endless series of expansions and contractions driven by this cosmic dance. The entire timeline of our universe, from its apparent beginning to its eventual heat death, is just one phase in an infinite series of cycles, all orchestrated by the motion of membranes in a hidden, higher dimensional reality. This idea expands even further when we consider how these extra dimensions might allow for time to be recycled not just in cycles, but in loops. If our brane is curved or warped within the bulk, it could potentially intersect with itself in complex ways. A path through the higher dimensional space might allow for a connection between two different points in our brain's timeline. This could create a closed timelike curve that doesn't require a wormhole in our familiar 4 dimensions, but instead uses a shortcut through an extra dimension. From our perspective, such a journey would be utterly inexplicable. An object would seem to vanish and reappear at an earlier time, but from the higher dimensional view, it simply took a different route through the geometry of the bulk. Our linear experience of time would be a kind of illusion, a product of being trapped on our brain, while the full, richer reality allows for connections that loop back on themselves. In this string-theoretic picture, our universe's timeline is not a solitary thread but one of many interconnected fibers in a vast, multidimensional tapestry, where the very concepts of beginning and end are woven into a much larger and potentially eternal pattern of existence. But if these grand theories of cosmic collisions and higher dimensional dances feel almost impossibly remote, a recent and stunning discovery in quantum physics has brought the concept of recycled time out of the theoretical cosmos and into the tangible reality of the laboratory. This is the world of time crystals, a new and exotic phase of matter that doesn't just exist in space, but actively and perpetually structures time itself, creating the closest thing we have to a microscopic, man-made time loop. To understand what makes a time crystal so revolutionary, we first need to grasp a fundamental principle that governs all of physics: symmetry. We are familiar with spatial symmetries. A snowflake looks the same when rotated by 60 degrees. A circle looks the same rotated by any amount. These are symmetries of space, but there are also symmetries of time. The most fundamental of these is time translation symmetry, which states that the laws of physics are the same today as they were yesterday and will be tomorrow. If you perform an experiment with identical conditions, you should get the same result regardless of when you do it. This symmetry is so deeply assumed that it underpins every scientific prediction we make. A time crystal shatters this assumption in the most elegant way possible. First predicted by Nobel laureate Frank Wilczek in 2012, and later created in labs using systems like diamond nitrogen vacancy centers and chains of ions, a time crystal is a quantum system that achieves periodic motion not in response to an external energy push, but in its ground state, its lowest energy state. In any normal system, if you remove all energy, it comes to a dead stop. A pendulum stops swinging. An electron settles into its orbital, but a time crystal, even in this ground state, refuses to be still. It exhibits persistent periodic oscillation, ticking away like a clock that never winds down. It's not creating energy from nothing that would violate the laws of thermodynamics. Instead, it's a stable, non-equilibrium system that has found a way to break time translation symmetry. The laws of physics are the same at all times, but the state of the time crystal is not. It has a preferred tick, a rhythm that defines a smallest unit of time for its existence, and it will repeat that rhythm forever without any further energy input. It is a structure in time, much like an ordinary crystal is a structure in space. This creates a fascinating form of a temporal loop on a quantum scale. The time crystal's components, be it a chain of atoms or a cloud of carefully tuned particles, are locked in a dance that endlessly repeats. Their quantum state cycles through a fixed sequence, returning to its starting point only to begin again, an eternal return playing out in a fraction of a second. This isn't time travel in the science fiction sense, but it is a literal, observable loop in the evolution of a quantum system. It is time recycled on a tiny but profound scale. For as long as the system can be maintained, its history is not a linear march forward but a tight, recurring cycle. This provides physicists with an unprecedented laboratory to study the physics of broken time symmetry and temporal order, offering a tangible model for how more complex loops might emerge in nature. The potential implications for our understanding of recycled time in the cosmos are immense. While a time crystal in a lab is a small, isolated system, it proves a radical principle that stable, perpetual motion through time is possible without violating the fundamental laws of physics. This opens the door to speculating that similar, though infinitely more complex, structures could exist in the fabric of the universe itself. Could the vacuum of space at a quantum level be seething with tiny, natural time crystals, each defining its own minuscule arrow of time? On a much larger scale, could the cyclic models of the universe, the bouncing cosmologies and colliding brains operate on a similar principle? Perhaps the universe itself, in its ground state, is not static but cyclic, with the Big Bang not being a one-time event but the beginning of just one tick in a cosmic-scale time crystal oscillation. The universe would then be the ultimate non-equilibrium system, perpetually cycling between expansion and contraction, its very existence a testament to broken time symmetry on the grandest possible stage. While this remains speculative, time crystals provide a mathematical and experimental foothold, a proof of concept that forces us to take the idea of recycled time from the realm of pure theory into a new domain of observable, testable physics, suggesting that the loops we imagine in the cosmos might be written into the same quantum rules that govern the smallest pieces of our reality. Yet for all the strange beauty of time crystals creating order in time, there exists an even more profound and bizarre quantum phenomenon that seems to stitch the very fabric of reality together in a way that completely defies our classical intuition. This is the enigmatic world of quantum entanglement, a connection so intimate and instantaneous that it challenges the core of what we thought possible, not just across space but across time itself. To understand this, we must revisit one of the most famous ideas in all of physics put forward by Albert Einstein. He described entanglement as spooky action at a distance, a phrase that perfectly captures the deep unease this concept can provoke. Imagine you have a pair of gloves. You take the left glove and put it in a box, and the right glove and put it in another identical box. You then send one box to the farthest reaches of the galaxy and keep the other here on Earth. According to our everyday logic, you wouldn't know which glove is where until you open a box. But once you open your box on Earth and see a left glove, you instantly know the one across the galaxy is the right glove. This isn't spooky, it's just simple deduction based on pre-existing properties. Quantum entanglement is nothing like that. In the quantum version, you don't have gloves, you have particles like electrons or photons. You create a pair of them in a single, shared quantum state, a sort of unified existence. Now you separate them by a vast distance, light years apart. Each particle is in a state of superposition, meaning its specific property, like its spin, is not determined. It is simultaneously spinning both up and down. It's as if each particle is both a left glove and a right glove at the same time. Now, here is the moment that baffled Einstein. The instant you measure one particle here on Earth and find it spinning up, the other particle, light years away, instantly collapses into a state of spinning down. The act of measurement here doesn't just reveal a property. It seems to dictate the property of its distant partner instantly, faster than the speed of light. This isn't a signal being sent. It is a fundamental, non-local connection that operates outside the bounds of space-time, a connection that suggests the two particles are not truly separate entities but remain parts of a single, unified whole regardless of the distance between them. This spooky action directly challenges two of the most cherished principles in classical physics, locality and realism. Locality is the idea that objects can only be influenced by their immediate surroundings, and any influence must travel through space, limited by the speed of light. Realism is the idea that objects have definite properties independent of whether we are observing them. Entanglement shatters both. The influence between the particles is non-local. It doesn't respect the speed of light limit. And the properties of the particles are not real and definite until the moment they are measured. This has been proven not as a philosophical thought experiment, but as hard, experimental fact through tests of Bell's theorem, closing the loopholes that might have preserved a classical, intuitive view of the world. The universe, at its heart, is fundamentally interconnected in a way that makes a mockery of our notions of separate, isolated objects in a static space. Now, if entanglement can create instantaneous links across vast spatial distances, could it also forge connections across time? This is where the concept of temporal non-locality enters the picture, and the implications are even more dizzying. If two particles can be entangled across space, why couldn't two events be entangled across time? Some interpretations of quantum mechanics, particularly the transactional interpretation proposed by physicist John Cramer, take this idea and run with it. In this model, every quantum event involves a kind of handshake across time. When a particle is measured here and now, it doesn't just send influence to its entangled partner across space, it sends a wave both forward and backward in time. A wave from the future travels back to the past to confirm the transaction, and the event is only realized once this loop in time is completed. This introduces the radical idea of retrocausality, where an effect in the present can reach back and influence a cause in the past. It's not that you could go back and prevent your own birth, creating a paradox. Instead, the universe would conspire to only allow transactions that are entirely self-consistent. The past and the future are not set in stone. They are in a constant, negotiated dialogue, with entanglement providing the lines of communication. This paints a picture of a quantum universe where the linear flow of time is an emergent property, a gross oversimplification of a much richer and more complex reality. At the fundamental level, past, present, and future are not neatly separated chapters but are deeply intertwined, all part of a single, interconnected quantum network. An event that we label as the cause and an event we label as the effect might be mutually defining, locked in a timeless embrace through quantum entanglement. This challenges the very foundation of causality, the bedrock of science and rational thought. It suggests that our experience of a clear, forward-moving timeline is a classical illusion, a story we tell ourselves about a reality that is, at its core, a vast web of atemporal connections. In this view, time isn't a river flowing in one direction. It's more like a complex, multi-dimensional tapestry where every thread is connected to every other thread, regardless of where our conventional timeline would place them. When we connect this to our overarching theme of recycled time, the possibilities become truly extraordinary. If the past and future are quantum entangled, then the universe could possess a form of cosmic memory or premonition encoded in its fundamental fabric. The low entropy beginning of the universe and its high entropy end might not be isolated events but could be quantum correlated, part of a single, self-consistent transaction that defines the entire cosmic cycle. In a cyclic model, the information from a previous universe might not need to be imprinted on a boundary or preserved through a bounce. It could be quantum entangled with the new universe from its very inception, with the Big Bang being the final confirmation of a transaction that began at the end of the previous cycle. The recycling of time would not be a mechanical process but a fundamental feature of a quantum reality where every ending is entangled with its beginning, ensuring a seamless and consistent loop of cosmic evolution. This suggests that the universe doesn't just repeat itself, it remembers itself, with every cycle being a new iteration of a timeless, quantum-correlated pattern, where the past is forever in dialogue with the future, and every moment is connected to every other moment in a magnificent, non-local and eternal now. But what if this intricate dance of entanglement and non-locality is just a hint of a much deeper, more fundamental truth about reality? What if our entire three-dimensional universe, with all its rich tapestry of stars, planets, and people, is actually nothing more than a projection, a holographic illusion emanating from a two-dimensional surface at the very edge of the cosmos? This is not science fiction. It is a serious, albeit mind-bending, theory derived from the study of black holes and the relentless laws of quantum mechanics. The holographic principle radically reimagines the nature of existence itself, suggesting that all the information contained within any volume of space, every particle, every force, every event that occurs, is not truly located within that volume at all. Instead, it is perfectly encoded on its lower dimensional boundary, like a three-dimensional movie being projected from a two-dimensional screen. This idea forces us to confront a staggering possibility. That time, the very framework of our experience, might not be a fundamental ingredient of the universe, but merely an emergent property, a side effect of this grand cosmic projection. The seeds of this revolutionary idea were planted in the fertile ground of black hole physics. As we discussed, when matter falls into a black hole, it seems to vanish behind the event horizon, taking its information with it and creating a paradox. But work by physicists like Jacob Bekenstein and Stephen Hawking showed that the maximum amount of information or entropy a black hole can contain is not proportional to its volume, as one might expect, but to the area of its event horizon. This was a profound clue. In an ordinary, non-gravitational system, entropy scales with volume. If you have a box of gas, a box twice the size can hold twice the information. But for a black hole, the most information-dense object possible, the limit is set by its surface area. This suggests a radical departure from how we think about information storage. It implies that all the information needed to describe the three-dimensional interior of a black hole is somehow stored on its two-dimensional surface. The black hole's event horizon acts like a cosmic hard drive, with each tiny plank-sized area on its surface acting as a single bit of information. The three-dimensional world inside is, in a sense, an illusion generated from this two-dimensional data. The holographic principle boldly extrapolates this finding to the entire universe. If it's true for a black hole, perhaps it's true for any region of space. Perhaps our entire observable universe is a holographic projection from a two-dimensional surface at its outer boundary, the cosmic horizon from which light has just had time to reach us since the Big Bang. In this view, you, me, the Earth, the galaxy, we are all akin to characters in an incredibly complex and immersive video game. The game appears to be three-dimensional, with depth and movement and time, but it is actually being rendered in real time from a two-dimensional source code located on the outermost shell of reality. Our perceptions of depth and solidity are a magnificent illusion. This doesn't mean the universe is fake. It means that the true, fundamental degrees of freedom of reality reside on this distant boundary, and what we experience is a projection of that data. This has a breathtaking implication for the nature of time. If the universe is a hologram, then time itself is part of the projection. On the boundary, the source code of reality might be timeless. The equations that describe this holographic correspondence, like the famous anti-de Sitter/conformal field theory, add S/CFT duality, suggest that the boundary theory is a quantum field theory that does not include gravity and may not have time as we know it as a fundamental element. Time, along with the third dimension of space, emerges from the complex interactions and correlations of the quantum data on the boundary. Our relentless experience of moving from past to future is like the illusion of movement in a movie. The film strip itself is static, a series of still frames, but when it is projected at a certain speed, the illusion of fluid, temporal motion is created. Similarly, our experience of time may be the result of the cosmic projector reading and interpreting the data on the boundary horizon, creating the seamless flow of the universe we inhabit. This perspective completely transforms how we might think about recycled time and cosmic cycles. In a holographic universe, a cycle of birth and death might not involve the physical collapse and rebound of three-dimensional space. Instead, it could be a process that happens on the timeless boundary. The information that describes one cosmic cycle could be processed, transformed, and then used as the initial data for a new projection. The end of a universe, its heat, death, or collapse, would correspond to the completion of one projection sequence. Then, a new set of initial conditions could be established on the boundary, and a new holographic universe, a new cycle of time, would be projected into existence. The three-dimensional universe with its new arrow of time would emerge anew, not from a singular point in space, but from a recalibration of the data on the cosmic film strip. In this model, time is not recycled through a physical bounce, but through an informational reset and reprojection. Each cycle is a new rendering from the same foundational source, a different movie played from the same cosmic projector, with the information from previous cycles potentially encoded in the new boundary conditions, leaving faint echoes or patterns in the holographic tapestry of the new cosmos. But if the universe truly is caught in an endless cycle of birth, death, and rebirth, where would we possibly look for evidence? How could the faint whisper of a previous cosmos possibly survive the unimaginable violence of a big crunch and the subsequent firestorm of a new Big Bang? The answer might be written across the entire sky, in the oldest light we can see, the cosmic microwave background. This faint, cold glow is the cooled remnant of the universe's fiery infancy, a snapshot of the cosmos when it was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. This radiation fills every cubic centimeter of space, a literal echo of creation, and it is in the subtle, tiny imperfections in this background, the temperature fluctuations that are mere millionths of a degree, that cosmologists search for clues not just about our universe's beginning, but about what may have come before. The search for these cosmic fingerprints is at the heart of Roger Penrose's conformal cyclic cosmology. If our universe is but one eon in an endless chain, and the end of the previous universe was transformed into the low entropy start of our own through conformal rescaling, then some information from that prior cosmos might have survived the transition. Penrose and his colleague Vargurdian proposed that the most dramatic events of that previous eon, the collisions of supermassive black holes, would have released titanic bursts of gravitational waves. These ripples in spacetime would have carried immense energy across the dying universe. When that universe was conformally rescaled to become our Big Bang, those gravitational waves would have been imprinted onto the new universe as slight variations in density, which later became the seeds for galaxy formation. Crucially, these imprints would not be random. The concentric ripples from a gravitational wave event would manifest in the CMB as series of perfectly circular patterns, regions of slightly lower temperature surrounded by rings of slightly higher temperature, like the quiet center of a pond after a stone has been thrown in. Finding such circles would be nothing short of revolutionary, a direct message from a time before time. It would be the ultimate evidence of recycled time, proving that our cosmos is not a one-off event but part of an eternal sequence. The implications would be staggering. It would mean that the information of the previous universe, the structure of its galaxies, the events of its history, is not completely lost but is encoded in the very fabric of our own reality. A cosmic palimpsest where the writing of a previous creation shows through beneath our own. This wouldn't just be a new chapter in cosmology. It would fundamentally change our understanding of existence, suggesting that time is not linear but circular, and that every ending is merely a prelude to a new beginning written with the same fundamental information. However, the search for these concentric circles has been fraught with controversy and immense challenge. The cosmic microwave background is an incredibly noisy signal, and extracting specific, subtle patterns from it is a Herculean task of data analysis. When Penrose and Gersadian first announced they had found evidence of these circles in data from NASA's WMAP satellite, the cosmological community met the claim with intense skepticism. Other teams analyzing the same data argued that the apparent circles could be produced by random chance, the result of the complex statistical methods used to process the map, or from other astrophysical processes within our own universe. The Planck satellite, which provided an even higher resolution map of the CMB, was subsequently used to test the hypothesis, and most analyzers concluded that the observed patterns were consistent with the random fluctuations predicted by the standard inflationary Big Bang model, finding no statistically significant evidence for Penrose's circles. The difficulty lies in the sheer complexity of the signal. The CMB is not a pristine, clean image. It is overlain with foreground contamination from our own galaxy dust and gas that emit their own microwave radiation, and from other galaxies. Teasing out a specific, weak pattern like concentric circles from this messy data requires sophisticated statistical techniques, and it is incredibly difficult to prove that any pattern found isn't just an artifact of the method itself. Furthermore, even if such circles were confirmed, alternative explanations within the framework of a single universe, such as certain types of sound waves in the early plasma, might be able to produce them. The quest for cycle echoes in the CMB is a perfect example of the cutting edge of science, where a breathtaking idea pushes our observational and analytical capabilities to their absolute limit, forcing us to develop ever more precise instruments and cleverer techniques to distinguish between a profound truth and a compelling illusion. Despite the current lack of consensus, the search continues, driving innovation and reminding us that the answers to the universe's deepest mysteries may be hiding in plain sight, etched in the faint, cold light that has been traveling to us since the dawn of time. Yet if the physics of looped time bends the mind, its philosophical implications threaten to unravel the very core of our human experience. For centuries, we have built our understanding of existence on the foundation of a linear timeline, a past that is fixed and unchangeable, a present where we exercise our will, and a future that is open and unwritten. This structure gives meaning to our choices, weight to our actions, and a sense of progress to our lives. But what happens to free will, to identity, to the very concept of meaning itself if time is a closed circle, endlessly repeating the same sequence of events for eternity? The idea that every joy, every tragedy, every mundane moment has already occurred an infinite number of times and will occur again forever is a concept so vast and alien that it challenges the pillars of our psychological and moral universe. This notion of eternal recurrence was most famously explored by the 19th century philosopher Friedrich Nietzsche, who presented it not as a scientific theory but as the ultimate existential test. He asked us to imagine a demon creeping into our loneliest loneliness and saying, "This life as you now live it and have lived it, you will have to live once more and innumerable times more, and there will be nothing new in it, but every pain and every joy and every thought and sigh must return to you all in the same succession and sequence." Nietzsche's question was not whether this is true, but how we would respond to the idea. Would we gnash our teeth and curse the demon, or would we respond with exultation, seeing this as the ultimate affirmation of life? For him, the goal was to live in such a way that you would welcome the endless repetition of every single moment of your existence, a concept he called amor fati, the love of one's fate. It was a call to embrace life in its totality, to live with such passion and purpose that the idea of reliving your life identically forever would be a cause for joy, not despair. But Nietzsche's thought experiment takes on a terrifying new dimension when viewed through the lens of modern cosmological theories. What if eternal recurrence is not just a metaphorical test of one's attitude toward life, but a literal, physical truth? In a truly looped universe, your choices are not truly yours. The feeling of free will is an illusion. You are an actor following a script written into the fabric of spacetime itself, performing the same lines in the same play on an infinite loop. Every decision you agonize over, every path you choose, is predetermined by the previous cycle. You will make the same mistakes, experience the same heartbreaks, and achieve the same triumphs over and over with no possibility of deviation. This presents a devastating challenge to our notion of moral responsibility. If you cannot choose otherwise, how can you be held accountable for your actions? The entire framework of ethics, built on the idea that we are autonomous agents making genuine choices, crumbles into dust. Praise and blame become meaningless in a universe where every action is a cosmic echo, forever rehearsed. This directly attacks our sense of identity and self. We construct our personal narratives from our memories and our capacity for growth and change. We are the sum of our experiences, learning from the past to build a better future. But in a looped timeline, there is no growth, only repetition. The person you are is not a unique, evolving consciousness but a fixed point in a cycle, a recording that plays and rewinds endlessly. This raises a haunting question: would each iteration of you even be aware of the cycle? If not, then from the perspective of each individual consciousness, life would feel exactly as it does now, linear and open-ended. Each cycle would be experienced as a first and only life, with no memory of the previous ones. But if awareness of the cycle were possible, the psychological burden would be unimaginable. Knowing that your suffering is predetermined and eternal could lead to the most profound nihilism, a paralysis of the will where effort and striving feel utterly pointless. Yet, perhaps there is another way to view this. If information is preserved across cycles, as theories like conformal cyclic cosmology suggest, then maybe the loop is not a perfect, identical repetition. Perhaps each cycle is a variation on a theme, with subtle differences evolving over vast eons. In this view, the universe itself could be learning, growing, and evolving through each iteration, and our lives, though part of a grand cycle, still contribute to this cosmic evolution. Our choices, while perhaps predetermined from a God's eye view outside of time, would still feel real and meaningful from within the cycle. This perspective offers a potential reconciliation, a universe that is both cyclic and meaningful, where the arrow of time within each cycle provides the necessary theater for consciousness, morality, and growth to play out, even if the entire production is part of a much larger, repeating festival. The philosophical implications of looped time force us to confront the most fundamental questions of all. What is the purpose of existence in a universe that might have no beginning, no end, and no ultimate linear narrative? The answer might be that we must create our own purpose, finding meaning not in the final outcome, but in the quality and character of each moment as it is lived, whether it is the first time or the 10,000th. But how do we move from these mind-bending thought experiments to a concrete, testable understanding of how time could actually loop? The bridge between philosophical speculation and physical possibility is built with the rigid, uncompromising tools of mathematics. To truly grasp how closed time-like curves or cyclic universes could function without collapsing into logical absurdity, we must delve into the abstract worlds of topology, differential geometry, and group theory languages that allow us to describe the shape of spacetime itself with exquisite precision. These are not just esoteric fields of study, they are the very frameworks that allow us to write the recipes for potential time machines and universe cycles on a chalkboard, long before we could ever hope to build one. At the heart of this endeavor is differential geometry, the mathematical language Einstein used to formulate his theory of general relativity. This branch of math doesn't deal with the simple, flat spaces of Euclidean geometry we learned in school. Instead, it provides the tools to describe and work with curved, dynamic surfaces. In this framework, gravity is not a force in the traditional sense, but a consequence of the curvature of spacetime. Mass and energy tell spacetime how to curve, and that curved geometry, in turn, tells mass and energy how to move. To model a closed time-like curve, a physicist doesn't write a science fiction story. They write down a metric, a mathematical object that defines the distance between points in a curved spacetime. Solutions to Einstein's equations, like the Gödel metric or the Kerr metric for a rotating black hole, are specific recipes for how matter and energy must be arranged to create a particular shape of spacetime. Some of these solutions, under very specific conditions, contain paths where the timeline, represented by a coordinate called t, loops back on itself. The mathematics doesn't care about paradoxes. It simply reveals that if you could arrange the universe in this particular way, these would be the consequences. This is where topology enters the picture. If differential geometry gives us the local details of the spacetime landscape, the hills and valleys topology gives us the global, big picture view. It's the study of properties that remain unchanged even when an object is stretched, twisted, or deformed, as long as it isn't torn. A coffee mug and a donut are topologically equivalent to a mathematician because one can be smoothly deformed into the other. They both have one whole. When applied to spacetime, topology helps us understand the overall connectivity of the universe. A universe with a closed time-like curve has a very different topology than our own. Its timeline isn't an infinite line, it's a circle. Topologists can classify the possible global structures of spacetimes that contain these loops, helping us understand the different kinds of time cycles that are mathematically permissible, regardless of the specific details of the gravity involved. Yet, simply finding a mathematical solution that allows for a time loop is only half the battle. The other, more daunting half is ensuring that solution is physically consistent. This is where the dreaded grandfather paradox moves from a narrative problem to a mathematical constraint. How can the equations ensure that events within a closed time-like curve are self-consistent? Imagine a billiard ball entering a time machine and traveling back to collide with its younger self, knocking it off course so it never enters the time machine in the first place. This is a logical inconsistency. The mathematics must somehow forbid such scenarios. Physicists like Igor Dmitrievich Novikov have proposed a self-consistency principle, which essentially states that the only events that can occur on a closed time-like curve are those that are entirely self-consistent. The equations themselves would have to resolve any potential paradox. In the billiard ball example, the only solutions that would be physically allowed are those where the ball emerges from the time machine and gives itself a gentle nudge, just enough to ensure it goes on to enter the time machine, but not so much that it prevents the event. The mathematics would show that the ball follows a single, unified, consistent trajectory that happens to include a loop with no true beginning or end to the sequence. The loop is a single, immutable event in the four-dimensional block universe. This quest for consistency often relies on the power of group theory, the mathematical study of symmetry. At its core, a time loop is a symmetry, a transformation that brings the system back to itself. Group theory provides the tools to understand how physical quantities and laws behave under such transformations. For a universe undergoing a cyclic evolution, like the conformal rescaling in Penrose's model or the brane collisions of string theory, group theory can describe the symmetries that are preserved from one cycle to the next. It can reveal what properties are invariant, what information could potentially be transmitted across a bounce, and how the fundamental laws of physics might remain unchanged or be subtly transformed from one eon to the next. The mathematics doesn't just tell us that time loops are possible. It provides a rigorous set of rules that any feasible loop must obey, acting as a cosmic editor that crosses out any plot lines that lead to contradiction and only green lights the stories that hold together from every possible angle. The profound mathematical elegance of looped time theories is undeniable, but science demands more than just beautiful equations. It requires hard evidence. How do we move from the chalkboard to the laboratory to test whether the fabric of time itself can bend into a circle? The quest to find empirical proof for these mind-bending concepts is one of the most daring and innovative frontiers in modern physics, pushing our technological capabilities to their absolute limits. Unlike testing a new particle or a distant star, we are attempting to probe the very framework of reality, and that demands a blend of sheer ingenuity and indirect detective work across multiple fields. One of the most direct approaches looks for hints of time reversal in the behavior of fundamental particles. Deep underground, in massive facilities like the Large Hadron Collider, physicists smash particles together at nearly the speed of light and meticulously analyze the debris. While they haven't found a full-blown time-reversed event which would look like particles spontaneously assembling into a heavier particle instead of breaking apart, they are searching for more subtle signatures. Certain rare particle decays are governed by the same CP violation that breaks time symmetry. By measuring the properties of these decays with exquisite precision, physicists are effectively conducting an ultra-high-precision test of how time's arrow operates at the most fundamental level. Any significant deviation from the predictions of the standard model of particle physics could be a clue that our understanding of time symmetry is incomplete, potentially opening a tiny window into processes where the arrow of time might be fraying or even looping on a quantum scale. Beyond smashing particles, another strategy involves listening to the cosmos with incredible sensitivity. As we discussed, the cosmic microwave background is a prime target in the search for evidence of a previous cosmic cycle. Experiments like the Simons Observatory and the proposed next-generation CMB-S4 project are designed to map the faint temperature and polarization fluctuations of this ancient light with unprecedented resolution. The hunt is not just for concentric circles, but for any statistical anomalies, patterns, or correlations in the data that seem to defy the predictions of standard inflationary cosmology. For instance, if the universe is truly cyclic, there might be a preferred direction or axis imprinted on the CMB, a kind of cosmic driftwood left over from a previous eon. Finding such a feature would be monumental, but the challenge is immense. The signal, if it exists, is incredibly faint and buried under foreground noise from our own galaxy and the subtle effects of gravitational lensing. Distinguishing a true cycle echo from a random statistical fluctuation or an unaccounted-for astrophysical effect requires not just better telescopes, but more sophisticated data analysis techniques than have ever been developed. Perhaps the most promising new arena for testing these ideas is not in the vastness of space or the depths of a particle collider, but on a well-controlled laboratory benchtop. The advent of quantum simulators and, as we explored, time crystals has opened a revolutionary new path. Quantum simulators are not general-purpose quantum computers. They are specialized systems, often using ultra-cold atoms or ions held in place by lasers, that can be programmed to mimic the behavior of other, more complex quantum systems. A physicist could, in theory, program such a simulator to model the quantum state of a tiny region of spacetime that contains a closed time-like curve. By observing how information flows and evolves within this simulated loop, researchers could test the mathematical consistency of these models and see if the paradoxical scenarios truly resolve themselves as theories like Novikov's self-consistency principle suggest. It's a way to experimentally probe the physics of time loops without needing to warp the entire universe. Time crystals themselves offer a tangible, albeit microscopic, example of a system that breaks time translation symmetry and exhibits periodic motion in its ground state. While not a time machine, a time crystal is a physical system whose structure repeats not in space, but in time. Studying how these systems interact with their environment, how they maintain their coherence, and whether more complex versions can be created, provides invaluable empirical insights into how temporal order can emerge and sustain itself. It's a living, breathing testbed for the kinds of physics that might govern a universe with recycled time on a much grander scale. The ultimate challenge in all of this experimental work is the sheer scale of the phenomena we are trying to detect. A time loop, whether in a rotating universe or a wormhole, likely requires energies and gravitational curvatures that are utterly beyond our current or even foreseeable technological reach. We are trying to find evidence for effects that may only manifest near the Planck scale or in the extreme conditions of a singularity. This forces scientists to be incredibly clever, looking for subtle, secondary effects that might trickle down into regimes we can observe. It's like trying to understand the shape of a vast mountain by studying a single grain of sand that has washed down from its peak. Each experiment, each observation, is a painstaking analysis of that grain, searching for a microscopic scratch that could only have been made by a specific, grand geological feature. The search for experimental proof of loop time is therefore a testament to human curiosity, a decades or even centuries-long project that requires patience, precision, and an unwavering belief that even the most profound mysteries of the cosmos are ultimately within our power to understand. While physicists and mathematicians weave complex theories about the nature of time, this profound fascination with breaking its linear chain is not confined to the laboratory. It is a theme deeply etched into the very heart of human culture, storytelling, and myth. Long before Einstein or Penrose put pen to paper, our ancestors were already dreaming of time loops, second chances, and eternal returns, using narrative to explore the possibilities and perils of a reality unshackled from a one-way arrow. This cultural conversation between science and story is a two-way street where fiction often presages theory, and theory, in turn, gives new depth and dimension to our oldest tales. We can trace this thread back to some of humanity's most ancient philosophies. The concept of eternal return or cyclical time is a cornerstone of many Eastern religions. In Hinduism, the universe undergoes endless cycles of creation, preservation, and dissolution, known as kalpas, each lasting billions of years. Buddhism teaches of samsara, the endless cycle of rebirth, where beings are reincarnated based on their karma until they achieve enlightenment. These are not merely abstract cosmological ideas. They are deeply personal, framing an individual's life within a vast, looping tapestry of existence. The goal is not to escape time entirely, but to escape the cycle of time, to achieve a state beyond birth and death. Similarly, ancient Greek philosophers like the Stoics entertained the idea that the universe would eventually repeat itself identically, with every event and person recurring again and again in an infinite loop. These myths and philosophies provided a framework for understanding the cosmos that was cyclical, not linear, offering a vision of time that was recyclable long before the term had any scientific meaning. In modern times, this exploration has found its most popular expression in science fiction and fantasy, where writers have used the time loop as a powerful narrative device to explore themes of fate, free will, and self-improvement. The most iconic example is undoubtedly the 1993 film Groundhog Day, where a cynical weatherman played by Bill Murray finds himself trapped reliving the same day in a small Pennsylvania town. At first, the loop is a personal hell, a prison of endless repetition. But as the cycles stretch into what some estimates suggest could be thousands of years, he is forced to confront his own flaws. The time loop becomes the ultimate crucible for transformation. He learns languages, masters piano, and ultimately shifts from selfishness to altruism. His redemption is only possible because time itself becomes a playground for practice, a space where the consequences of failure are erased with each new sunrise. The loop is not a punishment but a gift, the ultimate opportunity for a second, third, and 4,000th chance. Other stories have taken this premise in darker, more thrilling directions. Films like Source Code and Edge of Tomorrow use a time loop as a strategic tool to prevent catastrophe. A soldier or pilot relives the same brutal battle or terrorist attack over and over, using the knowledge gained from each failed attempt to eventually succeed. Here, the loop is a weapon, a way to hack causality and perfect a mission through grueling repetition. Television series like Russian Doll and The Magicians delve even deeper, exploring loops that are not just personal but interconnected, where the actions of one person in the loop can affect others, creating complex webs of cause and effect that challenge the very notion of a solitary experience. These narratives resonate because they tap into a universal human desire, the wish to go back and do things over, to correct a mistake, to say the right thing, or to simply have more time. They give us a fictional space to play out our deepest regrets and our most hopeful fantasies of mastery and control. This cultural obsession is more than just entertainment. It often serves as a conceptual playground that influences and is influenced by scientific thought. Science fiction authors, free from the constraints of peer review and experimental data, can imagine the implications of time loops with a creative liberty that sometimes anticipates theoretical physics. The concept of a closed timelike curve, for instance, was a staple of sci-fi time travel stories decades before physicists like Kip Thorne began seriously modeling traversable wormholes. Conversely, as theories like the multiverse or quantum retrocausality enter the public discourse, they provide fresh fodder for storytellers, who then reinterpret these ideas through a human lens, making the abstract mathematics emotionally relatable. A show like Dark on Netflix is a prime example, weaving an incredibly complex narrative involving time travel, causal loops, and multiple timelines that feels deeply informed by modern cosmological concepts, presenting them not as dry equations but as a heartbreaking family saga. This constant dialogue enriches both fields. Science provides the plausible mechanics, and fiction explores the profound human consequences, each pushing the other to think bigger, and ask deeper questions about the nature of reality and our place within it. Ultimately, this enduring fascination across cultures and centuries points to something fundamental in the human condition, a deep-seated yearning to break free from the tyranny of the clock. Linear time is the ultimate source of scarcity. There is never enough of it. It brings loss, aging, and the finality of death. The idea of recycled time, whether through spiritual rebirth, a cosmic cycle, or a personal time loop, is the ultimate rebellion against this scarcity. It represents a hope for renewal, for redemption, and for another opportunity to get things right. It is the dream of a universe that offers not just one chance, but infinite chances, where the story is never truly over, and the final page is always followed by a new beginning. Whether through the sacred cycles of ancient scripture or the comedic torment of a man trapped in Punxsutawney, we keep returning to this idea because at its core, it is a story about hope. The hope that our actions matter enough to be repeated, that our lives have meaning beyond a single, fleeting timeline, and that in the grand, mysterious workings of the cosmos, there might always be a way to start again. But this grand vision of an eternally recycling cosmos, of time perpetually renewing itself, runs headlong into one of the most formidable and unyielding principles in all of science, the second law of thermodynamics. This law, which gives us the arrow of time in the first place, seems to stand as an immutable barrier to any form of perpetual motion, even the motion of time itself. The second law states that the total entropy of a closed system always increases or at best remains constant, but it never decreases. Entropy is a measure of disorder, and the universe is on a one-way trip from the incredible order of the Big Bang to the ultimate disorder of heat-death. So, if the universe is truly cyclic, how can it possibly reset its entropy? How can the cosmic clock rewind itself without violating this most sacred of physical laws? This is the monumental challenge that any theory of recycled time must overcome, forcing us to ask whether a perpetual time machine is a physical possibility or a metaphysical fantasy. The core of the problem is often called the entropy problem. Each cycle in a model like Penrose's conformal cyclic cosmology or a bouncing universe must somehow begin with a low entropy state to establish a new, clear arrow of time. But if the previous cycle ended in a state of maximum entropy, a cold, empty, featureless void, where did that low entropy come from? It seems like getting something from nothing. Imagine a vast, chaotic junkyard. The second law says the junkyard can only get more chaotic over time. A cyclic model requires that this junkyard spontaneously reorganizes itself into a brand new, perfectly ordered factory, ready to start production again. From a classical thermodynamics perspective, this is utterly impossible. It would be like a shattered glass spontaneously reassembling itself on the floor or smoke pouring back into a cigarette. The laws of probability are overwhelmingly against it. There are almost infinitely more ways for a system to be disordered than ordered. Physicists have proposed several ingenious, though highly speculative, ways to circumvent this entropy problem. Roger Penrose's solution, as we touched on, is conformal rescaling. At the end of time, when the universe has expanded to near infinity and all matter has decayed into massless particles like photons, the concept of scale becomes meaningless. In this strange, stretched-out state, the universe effectively forgets how big it is. 1 billion years and a single second are physically equivalent. Penrose's mathematics shows that in this scale-free state, the incredibly high entropy end of one universe can be mathematically transformed or rescaled to become the incredibly low entropy beginning of the next. The entropy isn't being destroyed, it's being reset through a geometric trick that exploits the universe's loss of scale. It's not that the junkyard is being cleaned up. It's that the very definition of junkyard and factory are being reconfigured so that one becomes the other. Other models approach the problem differently. In the bouncing cosmologies predicted by loop quantum gravity, the quantum nature of spacetime itself provides a repulsive force that prevents the universe from collapsing into a true singularity of infinite density. The bounce happens at a finite, albeit enormous, density. At this point, the extreme quantum effects might fundamentally alter how we calculate entropy. It's possible that the gravitational field itself carries an immense amount of entropy, and that this entropy is somehow reset or reconfigured during the quantum bounce. The information of the previous universe isn't erased, but its thermodynamic impact might be scrambled, allowing for a new low-entropy beginning. Think of it as a cosmic hard reboot. The computer's memory isn't wiped, but the operating system is reloaded from a clean source, clearing the accumulated errors and conflicts that had slowed it down, providing a fresh start for a new session of cosmic computation. Yet, even if these mathematical models work, they push us to the very boundary of what we consider testable physics and into the realm of metaphysics. The question arises, is a universe that eternally recycles its time a form of perpetual motion machine? A perpetual motion machine of the first kind creates energy from nothing, violating energy conservation. A perpetual motion machine of the second kind, which is more relevant here, somehow reduces the total entropy of a closed system, violating the second law. So, does a cyclic universe violate these laws? Most physicists arguing for these models would say no, not exactly. They argue that the laws of thermodynamics, as we understand them, apply within each cycle, not necessarily to the entire multicycle system. The conformal rescaling or the quantum bounce acts as a kind of cosmic exception, a reset point that exists outside the normal thermodynamic rules that govern the universe during its life. The total entropy of the entire multicycle timeline might still be increasing when measured on a meta-time scale, or the definition of the system might be changed by the bounce itself. This is where the discussion becomes profoundly philosophical. If the universe can reset its own entropy through a mechanism that lies outside the domain of the laws it resets, are we still doing physics? Or have we entered a realm where our concepts of cause and effect, of before and after, break down entirely? The very idea of a cyclic universe challenges the notion of a truly closed system. Perhaps the universe is not all there is. Perhaps the reset mechanism requires something outside our universe, a higher dimensional bulk, a multiverse landscape, or a timeless mathematical realm to act upon it. In this view, our universe is not a perpetual motion machine. It is more like a piston in a larger engine, being reset by an external force we cannot yet see or describe. The search for a theory of recycled time forces us to confront the ultimate limits of our scientific understanding, questioning whether the laws we have discovered are truly universal laws or merely local bylaws that govern our particular cosmic epoch. It asks if time itself, in its endless striving for renewal, might ultimately be subject to a deeper, more fundamental principle that we have yet to uncover. But if the universe itself can be modeled as a timeless, four-dimensional block, then what is it that creates our powerful, universal sensation of a flowing now, a moving present that seems to slice through this static reality? This brings us to one of the most intimate and puzzling frontiers of this entire mystery, the human mind itself. Our conscious experience of time is not a passive recording of an external clock. It is an active, constructed process, a fragile mirage generated by the brain that may hold the key to understanding why time feels the way it does, and whether that feeling is a profound truth or a magnificent illusion. We don't just perceive time, we feel it. We feel the urgency of a deadline approaching, the nostalgia for a past summer, the anticipation of a future event. This psychological arrow of time is as powerful as the thermodynamic one, and neuroscience suggests it is built from a series of clever tricks the brain uses to make sense of the world. Think about how you experience the present moment. It doesn't feel like an infinitely thin mathematical point. It feels like a specious present, a window of about 2 to 3 seconds within which we integrate sensory information into a unified experience. This is why we can appreciate a melody not just as a series of isolated notes, but as a coherent phrase. The brain takes a stream of disjointed sensory data and stitches it together, creating a seamless narrative of what is happening now. It even edits this timeline to account for delays in neural processing. When you touch your nose and see your finger move, the signals from your eye and your skin arrive at the brain at slightly different times. Yet you perceive them as simultaneous. Your brain is constantly making small adjustments, creating a consistent and coherent story of the present, even if that story is a slightly post-drafted reconstruction of events that have already happened. Our sense of the flow of time may be the result of this continuous updating process, as the brain integrates new sensory information into its ever-evolving model of reality, creating the illusion of a present that is perpetually moving forward. This leads to a radical and captivating idea. What if the flow of time is not a feature of the external universe at all, but a product of our internal consciousness? In the block universe model, all moments, your birth, you reading this sentence, your eventual death exist with equal reality. There is no privileged now in the equations of physics. So why are we stuck in this particular moment, experiencing it so vividly, seemingly moving along the timeline? Some philosophers and scientists, like cognitive psychologist Donald Hoffman, propose that our perception of time is a user interface, a simplified dashboard constructed by evolution to help us navigate the world and survive. Just as a computer desktop uses icons of folders and files to represent complex binary code, our brains use the concepts of past, present, and future to represent a reality that might be far more strange and timeless. This interface hides the overwhelming complexity of the underlying reality, giving us a manageable, linear narrative that allows us to make plans, learn from consequences, and function effectively. If consciousness is the engine that generates the feeling of time's flow, then this opens a door to understanding how temporal loops might be experienced. In a universe with closed time-like curves or grand cycles, the physical structure might be a static, looped four-dimensional object, but a conscious observer traveling within that loop would still construct a linear narrative from their limited perspective. They would experience one moment after another, believing they are moving forward into an open future, even though their entire timeline is a fixed circle. Their consciousness would be the thread that weaves through the pre-existing beads of events, creating the illusion of progression. This suggests that even in a recycled cosmos, the experience of time would feel linear and real to any conscious being within it. The loop would only be apparent from a God's eye view outside of time itself. For the individual living it, each cycle would feel like a first and only life, a unique journey with a beginning, middle, and end, entirely unaware that their story is on an endless replay. This intertwining of consciousness and time leads to an even more speculative but fascinating possibility. That consciousness might not just perceive time but could play an active role in its manifestation. The controversial orchestrated objective reduction theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that quantum processes happening within the microtubules of brain cells are linked to the emergence of consciousness. Penrose further speculates that these quantum state reductions, which collapse probabilities into definite outcomes, are tied to the geometry of space-time itself. In this view, each moment of conscious experience could be a tiny quantum event that helps pin down a specific now from a fog of possibilities. While this theory is far from mainstream, it points toward a universe where mind and cosmos are not separate, where the flow of time and the flow of thought might be deeply connected, perhaps even two aspects of the same fundamental process. If that were true, then the recycling of time on a cosmic scale might be inseparable from the recycling of conscious experiences, suggesting that the universe is not just a physical system but an experiential one, endlessly generating moments of awareness within its eternal and possibly looped structure. For over a century, two monumental pillars have supported our understanding of the physical universe. On one side stands general relativity, Einstein's magnificent theory of gravity, which describes the cosmos on its largest scales, the graceful dance of planets, the warping of spacetime by galaxies, and the crushing depths of black holes. It is a theory of smooth, geometric curves where space and time are woven together into a single, dynamic fabric. On the other side stands quantum mechanics, the astonishingly accurate rulebook for the subatomic world, governing the behavior of particles, forces, and fields. It is a theory of probability, discreteness, and spooky connections, where things can be in two places at once and reality remains fuzzy until it is observed. Both theories are spectacularly successful in their own domains, but they speak completely different languages and are fundamentally, bitterly incompatible. Where they meet, at the center of a black hole or the instant of the Big Bang, the mathematics of physics breaks down into nonsensical infinities, signaling that our current understanding is incomplete. The quest to resolve this conflict, to find a single theory that can harmonize the cosmic and the quantum, is the holy grail of modern physics. This is the quest for quantum gravity, and its success or failure will determine our ultimate answer to the most profound question of all: what is the true nature of time? Each of the leading approaches to quantum gravity tackles the problem from a radically different angle, and in doing so, each forces time to undergo a startling transformation. Take string theory, one of the most famous contenders. It proposes that the fundamental building blocks of reality are not point-like particles but unimaginably tiny, vibrating loops of energy strings. Different vibrations of these strings correspond to different particles, elegantly unifying all forces and matter. But for the mathematics of these vibrating strings to work consistently, they require more room to move than our familiar 3 dimensions of space and 1 of time. String theory demands extra, curled-up spatial dimensions. In this framework, time is typically treated as a primitive, fundamental background against which the strings dance. However, some versions of string theory, particularly through the holographic principle we discussed, suggest that time, along with gravity, might actually be an emergent property, projected from a lower dimensional boundary where time itself may not be fundamental. This opens the door for time to be a secondary quality, something that arises from more basic quantum information, making the idea of it being looped or recycled a consequence of how that information is processed and projected across cosmic cycles. Then there is loop quantum gravity, or LQG, which takes a very different path. Instead of adding extra dimensions, it stays faithful to the core lesson of general relativity, that spacetime is dynamic but reimagines its very fabric. LQG proposes that space is not smooth and continuous but is woven from a network of finite, indivisible loops. Think of it as a cosmic mesh or a spin network, where area and volume come in tiny, discrete packets at the Planck scale. This has a breathtaking implication for time. In LQG, time is also quantized. It flows not as a smooth river but in discrete, tiny ticks, like the frames of a cosmic movie. But the most revolutionary aspect is how this approach deals with the beginning of time. The theory predicts that the gravitational collapse of a universe does not end in a singularity of infinite density. Instead, the repulsive force of quantum geometry becomes so powerful that it causes a big bounce. The universe reverses its collapse and begins expanding again. In this model, time is not created at a singularity. It is recycled through a quantum cosmic rebound. The arrow of time from a previous cycle is scrambled at the bounce, and a new arrow emerges with the new expansion, making time's renewal a fundamental prediction of the theory, not just a philosophical speculation. A third, and perhaps most radical, perspective comes from causal set theory. This approach suggests that the fundamental ingredients of reality are not particles or fields, or even space-time itself, but simple, discrete events. Imagine a vast cosmic heap of points. Each point represents a single event, a fundamental happening. These events are partially ordered by causal relationships. Which event can influence which other event? From this sparse, minimalist foundation, a set of events with a causal structure, our familiar, continuous four-dimensional spacetime is supposed to emerge. It is an illusion, an approximation that arises from the collective relationships between these fundamental events. In this view, time is not a thing that flows. The feeling of temporal passage is a consequence of this underlying network of causality. This framework handles the idea of looped time with remarkable elegance. A closed timelike curve would simply be a closed chain of causal links within the set, a circle of events where each one influences the next, eventually circling back to influence the first. Because the theory is fundamentally discrete, it avoids the nasty infinities and paradoxes that plague continuous spacetime models. Time loops are not strange anomalies. They are just particular, self-consistent configurations of the causal network, offering a paradox-free way to think about time being literally recycled within the fabric of reality. What all these diverse approaches highlight is a central, unifying theme in the search for quantum gravity: the demotion of time. In our everyday experience, time is the most fundamental stage upon which the drama of the universe plays out. But for many of these theories, time is not primitive, it is emergent. It is not a basic building block but a collective, approximate property that arises from the interactions of more fundamental, timeless entities, whether they are quantum bits of information, loops of gravitational field, or causal relationships. This suggests that the flow of time we feel so viscerally might be a compelling illusion, a story our brains tell us about a deeper reality where past, present, and future simply are. If time is emergent, then the possibility of it being recycled or looped becomes a question of geometry and information. Can the configuration of the fundamental elements arrange itself in a way that creates the illusion of a cyclic timeline? The answer from several corners of quantum gravity research is a resounding yes. The quest to unify gravity and the quantum is, therefore, much more than a technical problem in theoretical physics. It is a journey to the heart of our experience, promising to reveal whether time itself is a river we are sailing, or if we are merely the river, an ever-changing pattern in a timeless and perhaps endlessly repeating cosmic code. So if the universe's arrow of time is not a fundamental rule but a statistical fluke, a rare bubble of order in a sea of chaos, we are immediately faced with a deeply personal question. Why does our particular bubble have the specific properties that it does? Why do we experience a consistent flow from past to future and not some other arrangement? This line of inquiry leads us directly to one of the most fascinating and sometimes controversial concepts in modern cosmology, the anthropic principle. In its simplest form, the anthropic principle suggests that the observed properties of our universe must be compatible with the existence of observers who are here to observe them. We should not be surprised to find ourselves in a universe that has the right conditions for life, because in a universe that didn't, we simply wouldn't be around to wonder about it. It sounds almost trivial, like a tautology, but when applied to the vast ensemble of possibilities suggested by theories like eternal inflation, it becomes a powerful tool for explaining why our local reality looks the way it does, including the very nature of time itself. Consider the multiverse, that frothing ocean of bubble universes we discussed earlier, each with its own randomly selected physical laws and constants. In this infinite variety, the direction of time is just another variable. Some universes might have a strong, consistent arrow of time like our own. Others might have a weak arrow, where entropy increases so slowly that complex structures never form. Some might have no predominant arrow at all, existing in a timeless, chaotic equilibrium. And still others might have a reversed arrow, where what we call the Big Bang is actually their Big Crunch, and their entire history runs backwards from our perspective. Now ask yourself, in which of these universes could conscious, intelligent life evolve? The answer is almost certainly only in those with a strong and consistent arrow of time. The formation of stars, planets, and ultimately living organisms requires processes that are fundamentally irreversible. A star, for instance, is a giant engine that burns fuel, converting lighter elements into heavier ones and radiating energy out into space. This process increases entropy and defines a clear direction in time. In a universe without a reliable arrow of time, where cause and effect are constantly flipping, such long, stable, complex chains of events would be impossible. Planets couldn't form stable orbits around stars. Chemical reactions couldn't proceed predictably to build complex molecules, and neurons in a brain couldn't fire in a sequence that allows for thought and memory. Consciousness, as we understand it, seems to require a stable timeline. This means we should not be surprised that we find ourselves in a universe with a past-to-future flow. It is not that this direction is special or mandated by a deeper law. It is simply the only type of universe where beings like us can arise to take note of it. The anthropic principle acts as a cosmic selection effect. We are not seeing a representative sample of all universes. We are seeing the one slice of reality that is hospitable to our form of life. This perspective completely reframes the mystery of the arrow of time. The question is no longer, why does time have a direction? But rather, given that we exist, the direction of time in our region must be such that we can exist. The low entropy beginning of our universe, which seems so incredibly improbable, becomes a necessary precondition for our own existence, not a bizarre accident in need of a unique explanation. This line of thinking opens up a breathtaking possibility that universes with recycled or looped time could be incredibly common in the multiverse, but they would be barren, empty, and silent. They could be filled with fascinating physics regions where time forms perfect closed circles, or where entropy fluctuates wildly, but they would be devoid of any observers to witness these wonders. A universe with a tightly looped timeline, for instance, might reset itself every few million years. While such a universe could theoretically exist, any complex structures that began to form would be periodically wiped clean, reset back to a primordial state before sentience could ever emerge. These universes would be cosmic ghost towns, their intricate temporal mechanics playing out to an empty audience. Our own universe, with its relentless and linear march toward higher entropy, might seem dull by comparison, but it is this very dullness, this stability and predictability, that provides the long, uninterrupted runway necessary for life to accelerate into existence. The arrow of time, therefore, might be less a law of physics and more a requirement of biology, a necessary feature of any universe that contains beings capable of asking why it has that feature in the first place. But if the universe is truly a cosmic recycler, endlessly processing matter and energy through endless cycles of time, we are left with a profound and deeply puzzling question: what happens to the information? Not the matter itself, not the energy, but the specific, intricate quantum information that defines the state of every particle, every atom, every star, and every conscious thought. Is it too ground up and repurposed, or does it somehow persist, an eternal and indestructible record of everything that has ever been? To unravel this mystery, we must turn to the elegant and powerful framework of information theory, a field that began with the study of communication and data storage, but has since blossomed into a fundamental language for understanding the universe itself, revealing that information may be the most durable currency of all. At its heart, information theory is about the quantification of surprise. The more unexpected a message is, the more information it contains. But in physics, information takes on a far deeper meaning. The quantum state of a system, the specific position, momentum, and spin of its particles is information. This isn't just data in a ledger, it is the very code that defines reality. And one of the most bedrock principles of quantum mechanics is that this information can never be truly destroyed. It can be scrambled, hidden, or transformed into an incredibly complex form, but it can never vanish from the universe. This is the principle of unitarity, and it's as fundamental as the conservation of energy. If you could somehow reverse all the laws of physics, you could, in theory, take the final state of the universe and run the equations backwards to perfectly reconstruct its entire history. Every quantum event would be recoverable. This idea was put to its ultimate test by the black hole information paradox, which we explored earlier, and the resounding answer from modern physics, through ideas like black hole complementarity and the holographic principle, is that information wins. It always finds a way to be preserved. This brings us to a powerful concept known as the no-hiding theorem, a fascinating result in quantum information theory. It states that if information is lost from one part of a system, it cannot simply vanish into nothingness. It must be relocated to another part of the system or to the system's entanglement with its environment. There is no magical deletion button in the universe. The information isn't destroyed. It's delocalized, spread out, and woven into the finer details of the surrounding quantum correlations. Think of it like a document shredded into a million pieces. The information on the page isn't gone. It's just been transformed into a new, incredibly difficult-to-read format. The no-hiding theorem assures us that the shreds still exist. The information has not been erased from reality, only hidden in plain sight within the complex web of interactions. This theorem provides a crucial safety net for any theory of recycled time. It suggests that even if a universe undergoes a catastrophic collapse or a violent transition, the information from its previous cycle isn't annihilated. It might be encrypted beyond all recognition, but it is still there, waiting to potentially influence the new cycle. Now, apply this to our grand cosmic cycles. In Roger Penrose's conformal cyclic cosmology, the information from a previous eon isn't lost in the heat death. Through the process of conformal rescaling, the information encoded on the event horizons of supermassive black holes, the last structures to evaporate, is somehow transferred across the boundary to become the seeds of density fluctuations in the new Big Bang. The information is preserved, not in a recognizable form like ancient galaxies, but translated into the initial conditions of the new universe, in a bouncing cosmology like the one suggested by loop quantum gravity. The quantum bounce at the moment of maximum density might act as a kind of cosmic blender for information. The no-hiding theorem suggests that while the information is chaotically scrambled during the bounce, it is not erased. The specific history of the previous cycle is lost, but its quantum informational essence is imprinted onto the new expansion, perhaps determining the fundamental constants or the very laws of physics for the next cycle. In both cases, information is the enduring thread that connects the cycles, the cosmic constant that survives the death and rebirth of space-time itself. This leads us to the most staggering implication of all. If information is truly conserved and can be transmitted across cosmic resets, then it may be truly eternal and indestructible. Your experiences, your thoughts, the specific arrangement of atoms that makes you, the information that defines your existence, might not be a fleeting anomaly in an indifferent cosmos. In a universe with recycled time, that information could, in some abstract and profoundly transformed way, persist forever. It wouldn't be a conscious persistence. It wouldn't be an afterlife. It would be a physical fact. The quantum information that constitutes your being would be scrambled into the primordial soup of a new universe, perhaps later forming part of a new star, a new planet, or even a new conscious being in a future cycle, forever part of the endless, recycling tapestry of existence. This isn't a spiritual claim. It's a physical possibility emerging from the rigid laws of quantum mechanics and information theory. The universe might not remember you as a person, but it would remember the information that once made you up, ensuring that not a single bit of the cosmic story is ever truly lost, only endlessly rewritten into the next chapter of eternity. Yet to truly grasp how our universe could emerge with such a specific, life-friendly set of properties, we must venture back to the very first fraction of a second after its birth, to a period of unimaginable, exponential expansion known as cosmic inflation. This theory, a cornerstone of modern cosmology, was proposed to solve several profound puzzles about our universe, such as why it appears so remarkably flat and uniform in every direction we look. The idea is that a tiny, subatomic patch of space, filled with a peculiar high-energy field called the inflaton field, underwent a sudden and spectacular growth spurt, doubling in size over and over again in a dizzying sequence, smoothing out any initial wrinkles and seeding the tiny density fluctuations that would one day become galaxies. This inflationary burst set the stage for everything that followed, providing the clean, low-entropy starting point that established the arrow of time we experience today. But this incredible event, which seems to mark a definitive beginning, might itself be part of a much larger and potentially endless cycle, where the beginning of time is not a singular point but a recurring phase in an eternal cosmic rhythm. This possibility emerges from a fascinating extension of the inflation idea known as eternal inflation. Imagine the inflaton field not as a placid lake, but as a wildly turbulent and bubbling ocean. In most models, the inflaton field eventually loses its energy, decaying into the particles that fill our universe and bringing the inflationary period to a graceful end. But what if this decay doesn't happen everywhere at once? The quantum nature of the inflaton field means it is subject to constant, random fluctuations. In some regions, the field might drop to a lower energy state, ending inflation and creating a stable, expanding universe like our own, a single bubble of calm in a chaotic sea. But in other regions, the quantum fluctuations might push the field back up, causing inflation to continue at a frantic pace. This means that while inflation is ending here, creating our pocket of reality, it is continuing relentlessly elsewhere, creating ever more space and spawning an infinite number of other bubble universes. This process is, for all intents and purposes, eternal. It has no end, and it may have had no true beginning, creating a multiverse of inconceivable diversity where each bubble has its own unique physical laws and, crucially, its own unique relationship with time. Within this framework of eternal inflation, the concept of recycled time takes on a breathtaking new dimension. Each of these bubble universes is born from a quantum fluctuation within the eternally inflating background. Since the properties of each bubble are determined randomly, some of these universes might naturally form with geometries or matter content that allows for closed timelike curves, regions where time loops back on itself. In such a bubble, time wouldn't just have a direction, it would have a built-in cycle. Furthermore, the process of bubble nucleation itself could be cyclic. Some models suggest that these bubbles don't just form and expand. They can also collide with each other, or even with the inflating background, in ways that trigger new periods of inflation within them. A universe could undergo its own internal inflationary phase, settle down, and then, through some catastrophic event or quantum transition, have a new inflattened field become excited, launching a new inflationary burst that effectively resets its own expansion and potentially its arrow of time. In this view, a single universe within the multiverse could experience its own series of internal cycles, a Russian doll of inflationary periods where time is recycled not on a cosmic scale of universal collapse and rebirth, but through a series of grand internal resets. This leads us to the most profound question of all. Did time have a definitive beginning, or is it truly eternal? The standard hot Big Bang model points to a singularity, a point of infinite density where the laws of physics break down, as the absolute beginning of time. Cosmic inflation was originally proposed to avoid this singularity, replacing it with a finite, albeit incredibly dense, state. But does inflation itself require a beginning? The theory of eternal inflation offers a compelling answer: perhaps not. If the inflating state is eternal into the future, could it also be eternal into the past? This is a much trickier proposition, but some models, like the idea of an eternal inflationary plateau, suggest that the inflattened field could have always existed in a high-energy state, constantly generating new pocket universes without ever having a singular starting point. In this scenario, time has no beginning. Our universe has a beginning within this eternal meta-time, but the larger multiversal structure exists forever without a creation event. The question of what happened before the Big Bang becomes meaningless because time itself, in its fullest multiversal sense, did not have a starting gun. It was always ticking. Our linear experience of time, with its clear beginning, is just a local phenomenon within our bubble, a small chapter in an infinite, unchronicled book. But to truly understand how time could be recycled not just for the cosmos, but for you and me personally, we must venture beyond the realm of quantum information and step into one of the most experimentally verified and mind-bending domains of physics, Einstein's theory of relativity. This is where we discover that time is not a universal metronome ticking at the same rate for everyone everywhere. Instead, it is a deeply personal and malleable experience, a river that flows at different speeds depending on how fast you're moving or how deep a gravitational well you're in. This revelation doesn't just change how we think about clocks, it fundamentally reshapes how we might imagine personal time loops and their relationship to a potentially recycled cosmic time. The effects are most clearly seen in what physicists call time dilation. According to Einstein's special theory of relativity, the faster you move through space, the slower you move through time relative to someone who is stationary. This isn't a mechanical error or an illusion, it's a fundamental property of spacetime itself, Imagine a pair of identical twins. One twin stays on Earth living a normal life. The other twin boards a spacecraft and journeys to a distant star at a significant fraction of the speed of light. For the traveling twin, time on the ship would feel perfectly normal. They might read a book, have a meal, and feel like a few hours have passed. But when they return to Earth, they would step out of their ship to find that decades or even centuries had gone by. Their Earth-bound twin would be old or long gone, while they remain nearly the same age. This is the famous twin paradox, and it has been confirmed countless times with incredibly precise atomic clocks flown on airplanes and satellites, which tick ever so slightly slower than their counterparts on the ground. Time is literally stretched by motion. General relativity adds another layer to this personal time warp: gravity. The stronger the gravitational field you're in, the slower time passes. A clock at sea level, closer to Earth's mass, will tick slower than a clock on a mountaintop. This effect, too, is confirmed daily. The GPS system in your phone must constantly correct for the fact that the atomic clocks on the satellites in orbit, experiencing weaker gravity, tick faster than clocks on the ground. If they didn't, your navigation would be off by several miles within minutes. So, your personal experience of time is not just your own, it's tied to your state of motion and your address in the universe's gravitational landscape. There is no single now, there are only countless personal nows, each valid for the observer experiencing them. This concept, known as the relativity of simultaneity, is perhaps the most profound lesson of all. Two events that appear to happen at the same time for one observer can occur at completely different times for another observer, moving at a different velocity. There is no privileged frame of reference to declare a universal present moment. This shatters the classical notion of a cosmic clock that everyone can agree on. The universe does not have a single, scrolling timeline. It is more like a vast, four-dimensional block where past, present, and future are all equally real, and different observers simply slice through this block at different angles, each carving out their own unique sequence of nows. This block universe view is a natural consequence of relativity, and it suggests that the flow of time we feel might be a psychological artifact, not a fundamental feature of the external world. Now, weave these relativistic effects into the concept of a looped or recycled universe, and the possibilities become staggeringly complex and rich. In a cosmos that undergoes grand cycles, the recycling of time might not be a uniform process experienced identically by every particle. Relativity suggests that personal timelines could become twisted and knotted relative to the cosmic timeline. Imagine a civilization living on a planet orbiting a star that is falling into a supermassive black hole at the end of a universal cycle. Due to the intense gravitational time dilation near the black hole's event horizon, their final moments could be stretched out from their perspective to last for billions of years of cosmic time. They could effectively witness the entire death of their universe, the conformal rescaling, and the birth of the next big bang from their own slowed-down reference frame, their personal timeline bridging the gap between cosmic cycles. For them, the end of one universe and the beginning of the next are connected events in their personal history, while for an observer in deep space, those events are separated by an eternity. Furthermore, the existence of closed timelike curves, those loops in spacetime permitted by general relativity, takes on a new light when viewed through the lens of personal time. An astronaut traveling on such a curve would return to their own past, but their personal biological clock would have recorded the duration of the journey. They would have experienced a finite amount of time, say 10 years, only to emerge at the spacetime event from which they launched, perhaps only 10 minutes after they left from the perspective of a stationary observer. Their personal timeline would form a closed loop, but it would be a loop with a duration, a lived experience. This creates a fascinating blend of linear and circular time. From a God's eye view outside the loop, their entire history is a static, unchanging knot in space-time. But from their own first-person perspective, they would live a linear, conscious life that happens to end exactly where it began, with the potential to have new experiences and make new decisions on each loop, even if the larger universe around them is locked in an eternal recurrence. The recycling of time becomes not just a cosmic phenomenon, but an intimate, personal one, where an individual's timeline can become detached from the mainstream flow of cosmic history and woven into its own independent, repeating pattern. But if the relentless expansion driven by dark energy is the dominant force shaping our cosmic future, what does that mean for the possibility of time itself being recycled? For decades, cosmologists have pondered the ultimate fate of the universe, and their predictions have largely revolved around a cosmic tug of war between two opposing forces, the outward momentum of the Big Bang and the inward pull of gravity. The discovery of dark energy in the late 1990s dramatically shifted the balance of this struggle. This mysterious force, making up about 68% of the universe's energy density, acts as a kind of anti-gravity, causing the expansion of space to accelerate rather than slow down. We don't know what dark energy is, but we can observe what it does, and its behavior is the single most important factor determining whether the universe will end in a way that allows for a rebirth or concludes with a permanent, silent finale. This acceleration points toward several possible endings, each with profound implications for time. The first is the heat death or the big freeze. In this scenario, dark energy continues to push galaxies apart at an ever-increasing rate. Eventually, all stars will burn out and all black holes will evaporate via Hawking radiation. The universe will become a vast, cold, and incredibly dilute soup of low-energy particles, achieving a state of maximum entropy. With no energy gradients left, no hot spots or cold spots, no further work can be done. The universe will be in a state of perfect equilibrium, and all processes, including the experience of time, will effectively grind to a halt. The arrow of time, which depends on increasing entropy, will cease to have any meaning because entropy cannot increase any further. This is the ultimate victory of disorder, a static, timeless end that seems to slam the door shut on any notion of recycling. A more violent alternative is the Big Rip. This fate awaits us if the strength of dark energy, characterized by a parameter called its equation of state, is particularly potent. In this model, the accelerating expansion doesn't just move galaxies apart. It becomes so powerful over time that it overwhelms all other forces. First, galaxy clusters would be torn apart, then individual galaxies. As the end draws near, the expansion force would rip stars from their solar systems, and then planets from their stars. In the final moments, even atoms and atomic nuclei would be shredded apart by the accelerating fabric of space itself. The universe would end not with a whimper, but with a C, a T, a S, T, R, O, P, H, I, C, Chinese letter of every single structure down to the subatomic level. This is a definitive and absolute end, leaving behind nothing but a barren, expanding void of fundamental particles unable to ever interact again. A Big Rip doesn't just end the universe, it annihilates the very stage upon which any new physics could play out, making a cyclic rebirth seem impossible. For a long time before dark energy was discovered, the favored model was the Big Crunch. This was the classic cyclic scenario. If there was enough matter in the universe, gravity would eventually halt the expansion and reverse it. All galaxies would come rushing back together, space would contract, and the universe would collapse back into a hot, dense state mirroring the Big Bang. This singularity could then serve as the springboard for a new Big Bang, a new cycle of expansion and contraction in an endless cosmic heartbeat. Dark energy, with its repulsive force, seems to have robbed us of this elegant symmetry. The acceleration it causes appears to make a gravitational reversal impossible, dooming us to an ever-expanding, dissipative future instead of a restorative collapse. The discovery of dark energy, therefore, was initially seen as a death knell for simple cyclic models of the universe. However, all is not lost for the dream of recycled time. Our understanding of dark energy is still in its infancy. We measure its current effect, but we do not know if its strength is constant or if it evolves over time. This uncertainty opens a critical back door for cyclical theories. What if dark energy is not constant? Some theoretical models propose a form of dark energy that decays over time. Imagine a universe where dark energy drives a long period of accelerated expansion, but its influence gradually fades away. After trillions of years, gravity, primarily from dark matter, could reassert its dominance. The expansion would slow, stop, and finally reverse, leading to a big crunch after all. This would elegantly incorporate dark energy into a cyclic model, not as an obstacle, but as a mere phase in a much longer cycle. The accelerated expansion would be the universe's way of resetting itself, spreading matter and energy so thin that when gravity finally takes over again, the subsequent collapse would be into a smooth, uniform state, perfect for triggering a clean bounce and a new beginning. Another fascinating possibility comes from the nature of the vacuum of space itself. In quantum field theory, what we call empty space is not truly empty. It is a seething foam of virtual particles popping in and out of existence. This vacuum has an inherent energy density which could be the source of dark energy, but this vacuum state might not be the most stable state possible. Our universe could be in a false vacuum, a temporarily stable but ultimately metastable state, like a ball resting in a small dip on the side of a much larger hill. A random quantum fluctuation could someday cause our local vacuum to tunnel into a true, lower energy vacuum state. This event would create a bubble of true vacuum that expands outward at the speed of light, fundamentally altering the laws of physics within it. This would be a definitive end for our universe as we know it, but it could also be a beginning for something new. The new vacuum could have entirely different properties, potentially giving rise to a new cosmic cycle with its own arrow of time. In this multiverse perspective, the death of one universe by vacuum decay could be the birth of another, a different form of recycling mediated by the evolution of the dark energy field itself. The interplay between dark energy and the arrow of time is subtle yet profound. The arrow of time is fueled by low entropy initial conditions and the subsequent journey toward disorder. Dark energy, through its acceleration of the expansion, actually influences how efficiently the universe can produce entropy. As galaxies are pushed apart beyond each other's cosmic horizons, the amount of entropy the universe can potentially reach in the far future is vastly larger than it is today. In a way, dark energy is ensuring that the universe has a very long and productive future for entropy generation, solidifying the arrow of time for eons to come. However, this very process seems to lead to a dead end. A cyclic universe needs a way to reset its entropy, to wind the clock back down. The great challenge for modern cosmology is to find a physically plausible mechanism that can overcome dark energy's tendency to drive the universe toward a maximum entropy state and instead create the conditions for a new low entropy beginning. Whether through the decay of dark energy, a quantum bounce at the Planck scale, or a vacuum transition, the ultimate fate of time rests on the mysterious nature of this dark force that currently dominates our cosmos. determining if our story is a one-off novel or a volume in an infinite series. But to truly understand how the sharp, definite world of our experience emerges from the fuzzy, probabilistic quantum realm, we must venture into one of the most crucial processes in all of physics, quantum decoherence. This is the mechanism that explains why we don't see cats that are both alive and dead, why tables and chairs have definite positions, and most importantly for our journey, how the smooth, irreversible flow of time we perceive comes to dominate our reality. At its heart, decoherence is the story of how quantum systems lose their special wave-like properties, their coherence, and start to behave like the familiar, classical objects we interact with every day. It is the process that creates the boundary between the quantum weirdness of the microscopic world and the stable, predictable world of the macroscopic, and it may hold the key to understanding how time itself emerges from a timeless foundation. To grasp decoherence, imagine a perfect, isolated quantum particle like an electron. This electron can exist in a state of superposition, meaning it can be in a combination of multiple states at once, say, spinning both clockwise and counterclockwise simultaneously. This is its coherent state. Now, imagine that this electron is not alone in the universe. It is constantly bumping into other particles, even if it's just the photons of light or the molecules of air in an otherwise empty-seeming room. Each time it interacts with its environment, a tiny piece of information about its state is imprinted onto the environment. The environment effectively measures the electron. After countless trillions of these interactions, the environment becomes a vast, permanent record of the electron's state. But here's the catch: this process is irreversible. The information about the other possible states, the other parts of the superposition, is not destroyed, but it is scattered into the environment in a way that is practically impossible to gather back together. The different possibilities can no longer interfere with each other. The electron appears to have chosen a definite state. From our perspective, the superposition has collapsed and a classical, definite reality has emerged. This isn't a magical collapse caused by consciousness. It's a practical, physical process driven by relentless interaction with the surrounding world. This irreversible scattering of quantum information into the environment is deeply tied to the arrow of time. The process of decoherence generates entropy. When the electron was in its pure, coherent superposition, it was in a state of low quantum entropy, a very specific and ordered state. As it interacts with the environment and becomes entangled with it, that quantum information is delocalized. The overall system, now including the environment, moves to a state of higher entropy. This increase in entropy, driven by decoherence, gives a clear direction to time for that specific quantum event. Once the information is scrambled into the environment, it is extraordinarily unlikely for it to spontaneously unscramble itself. The quantum dice have been rolled and the result is recorded. This is why we see teacups shatter and never reassemble. The countless quantum decoherence events that occur as the shards fly apart and interact with the air irrevocably record the event of the breakage, making its reversal a statistical impossibility. In this way, the relentless process of decoherence at the quantum level is the microscopic engine that drives the macroscopic arrow of time we experience every second of our lives. Yet, if decoherence is what makes time's arrow so persuasive, could the process itself ever be reversed, creating a local arrow of time that points backward or even loops? The laws of quantum mechanics are, in principle, time-symmetric. If you could somehow reverse the motion of every single particle involved in a decoherence event, the electron and every photon and atom it interacted with, you could, in theory, reverse the process. The scattered information would coherently refocus, and the superposition would be restored. This is known as quantum recoherence, but achieving this is fantastically difficult in practice. It would require perfect control over an unimaginably vast number of particles in the environment, a feat far beyond any conceivable technology. It's the difference between unscrambling a single egg and gathering every single splatter of a dropped omelette from the floor, the walls, and the ceiling and perfectly reassembling it back into the egg. The probability is so vanishingly small that for all practical purposes, decoherence is irreversible, and the arrow of time it creates is absolute. However, the realm of practical impossibility is where physics gets truly interesting. While reversing decoherence for a large, warm, messy object like a shattered vase is hopeless, physicists have achieved remarkable feats of recoherence in highly controlled laboratory settings. Using isolated quantum systems like individual atoms or ions held in electromagnetic traps and cooled to near absolute zero, they can shield them from their environment. In this pristine setting, they can deliberately introduce an interaction to cause decoherence, and then, with exquisite precision, use complex laser pulses to effectively reverse the interactions, undoing the decoherence and restoring the lost coherence. It's like hitting rewind on a quantum videotape. This doesn't violate the second law of thermodynamics because the experimenters are putting energy and information into the system to achieve this reversal. They are not a closed system. But it proves a profound point. The quantum arrow of time established by decoherence is not fundamentally absolute. It is a consequence of the practical difficulty of controlling a complex environment, not a deep law of nature. This laboratory trickery opens a breathtaking window into how time might be recycled on a quantum scale. Imagine a hypothetical, perfectly isolated quantum universe, a tiny cosmic bubble where a small number of particles interact. In this bubble, the process of decoherence and recoherence could, in theory, happen spontaneously. A quantum fluctuation could cause the system to decohere, establishing a local arrow of time where events play out in one direction. Then another fluctuation could cause a recoherence, effectively resetting the quantum clock and allowing the sequence to play out again, or even in reverse. In this microscopic realm, time would not be a one-way street. It would be a pulsating, oscillating thing with arrows of time that could form tiny, closed loops. The boundary between the coherent quantum world and the decohered classical world would become fuzzy and permeable. This wouldn't be time travel in the science fiction sense, but it would be a form of temporal recycling where the very definition of before and after could lose its meaning within the loop. Connecting this back to the cosmos, these quantum-scale time loops could be the fundamental seeds for larger recycled time structures. In the bizarre conditions of a black hole singularity, or at the moment of a cosmic bounce, where the classical description of spacetime breaks down, quantum gravitational effects might dominate. In this realm, the very distinction between a particle and its environment might blur. The extreme conditions could allow for vast, spontaneous recoherence events, where quantum information that was thought to be lost is recovered on a cosmic scale. This could provide a mechanism to reset the entropy clock, not through a geometric trick like conformal rescaling, but through a fundamental quantum process that reverses the arrow of time from the bottom up. The universe wouldn't just be reborn, it would be quantum mechanically refreshed with its decoherence history wiped clean, ready to establish a new arrow of time and a new classical reality from the timeless, coherent soup of quantum possibilities. The emergent flow of time we hold so dear may not be a river flowing inexorably to the sea, but a wave on a vast ocean, rising and falling in eternal, quantum-driven cycles. Long before telescopes peered into the depths of space or equations were scribbled on blackboards, humanity was already gazing at the heavens and contemplating the nature of time itself. And for countless ancient cultures, the message written in the cyclical movements of the sun, moon, and stars was unmistakably clear. Time is not a straight line, but a circle. This profound intuition, born from careful observation of the natural world, forms the deepest roots of our modern scientific theories of recycled time. The Maya of Mesoamerica, for instance, were master timekeepers, developing a complex system of interlocking calendars that tracked cycles within cycles. Their long count calendar measured vast epochs, and the completion of one such cycle in 2012 sparked global fascination, often misinterpreted as a prophecy of doom, but truly representing their belief in the cyclical renewal of ages. For the Maya, time was not linear progress but a series of repeating patterns, where the end of one period seamlessly ushered in the beginning of the next, a concept not so different from the conformal rescaling in Roger Penrose's Cosmology. Across the ocean, the ancient Greeks were wrestling with similar ideas, though through a more philosophical lens. In the 6th century before the Common Era, the pre-Socratic philosopher Heraclitus famously declared that you cannot step into the same river twice, emphasizing constant change. Yet he also suggested this change was part of a grand cyclical order, an eternal process he called the ever-living fire, kindling in measures and going out in measures. Later, the Stoic philosophers fully embraced the concept of eternal recurrence, proposing that the universe would be consumed by fire in a great conflagration, only to be reborn exactly as it was before, with every event and every person destined to play out their lives again in an infinite loop. This was not a scientific hypothesis but a metaphysical one, a test of one's character. Could you affirm your life knowing you would live it again, identically, forever? This philosophical challenge would echo millennia later in the thoughts of Friedrich Nietzsche. These cyclical cosmologies were not mere abstract speculations. They were deeply woven into the religious and cultural fabric of these societies. In Hinduism, the concept of time is described through immense cycles called kalpas and yugas, each lasting for billions of years. A single day of the creator god Brahma is a kalpa, a period of creation that is followed by a night of equal length, a period of dissolution. This endless rhythm of creation, preservation, and destruction mirrors the life cycle of any living being, but on a cosmic scale. The universe itself is seen as a living, breathing entity, eternally cycling through birth, death, and rebirth. Similarly, Buddhism's concept of samsara, the wheel of rebirth, places each individual within a vast karmic cycle, where the consequences of one's actions determine one's future existences. The ultimate spiritual goal is to break free from this wheel, to achieve nirvana, a state beyond the cycles of time and suffering. In these Eastern traditions, the recycling of time is not just a physical process but a deeply moral and spiritual one, where the cosmos and the individual soul are inextricably linked in a journey toward liberation. The ascent of Abrahamic religions in the West, particularly Christianity, introduced a powerful and competing linear narrative of time. This world, you presented a definitive beginning, Genesis, a central, unique event in history, the crucifixion of Christ, and a prophesied end, the apocalypse and final judgment. Time became an arrow with a purpose, a story of fall and redemption moving toward a final, telos or end goal. This linear framework provided the philosophical underpinning for the idea of progress that would later fuel the scientific revolution. Why look for cycles when history was a unique drama moving toward a singular conclusion? For over 1,000 years, this linear view dominated Western thought, pushing cyclical models to the philosophical fringe. Yet the old ideas never completely vanished. They simmered beneath the surface, waiting for a new context to give them fresh life. That new context arrived with the scientific revolution itself, as astronomers like Johannes Kepler and Nicolaus Copernicus, who meticulously charted the cyclical motions of the planets, began to unknowingly lay the groundwork for a return of cyclical time on a scientific, rather than mythological, basis. The true resurgence of cyclical time in the West had to wait for the profound cosmological shifts of the 20th century. The formulation of the second law of thermodynamics gave us the arrow of time, but it also presented the bleak picture of the heat death of the universe, a definitive and final end. For some scientists, this absolute finale was philosophically unsatisfying. The first major modern scientific model for a cyclic universe came from the influential physicist Richard Tolman in the 1930s. He addressed a critical flaw in earlier Newtonian ideas of a simply bouncing universe, the problem of entropy. Each cycle would generate more entropy, so subsequent cycles would be longer and less intense, like a ball bouncing lower each time until it stops. Tolman's oscillatory universe model attempted to find a mechanism within the framework of Einstein's relativity to allow for true cycles, though the entropy problem remained a formidable obstacle. His work was crucial because it moved the concept from philosophical speculation into the realm of theoretical physics, treating the universe as a dynamic system that could be modeled with equations. The latter half of the 20th century saw an explosion of new ideas that provided fresh mechanisms for cosmic recycling. The development of quantum mechanics and the discovery of the Big Bang's afterglow, the cosmic microwave background, gave cosmologists new tools and new data. The theory of cosmic inflation, proposed by Alan Guth and others, explained the universe's initial conditions but also gave rise to the stunning concept of eternal inflation and the multiverse, an ensemble of universes, each potentially with its own laws of physics and its own relationship with time. This wasn't a single cyclic universe, but a meta-cycle of endless creation. Then came string theory and its vision of colliding brains, providing a dramatic new mechanism for a Big Bang that was not a beginning but a collision in a higher dimensional space. Finally, loop quantum gravity's prediction of a big bounce, where quantum geometry prevents a singularity and causes a rebound, offered a purely quantum gravitational path to a cyclic cosmos. Each of these modern theories, in its own way, is a direct descendant of those ancient intuitions, a scientific reimagining of the Mayan calendar round or the Hindu kalpa, using the language of mathematics instead of myth. What is it about the idea of circular time that has proven so incredibly durable, persisting for thousands of years across wildly different cultures and scientific paradigms? Its appeal seems to tap into something fundamental within the human psyche. On a psychological level, cycles are comforting. They promise renewal, the return of spring after winter, the dawn after the darkest night. They offer a sense of order and predictability in a seemingly chaotic universe. The linear model, with its definitive end, can feel nihilistic and final, while the cyclical model suggests that endings are always preludes to new beginnings. It is a narrative of hope and eternal potential. Furthermore, a cyclic universe diminishes the anxiety of a single, linear history where every mistake is permanent. If the universe repeats, then so do opportunities. There is a sense of cosmic second chances woven into the fabric of reality itself. This enduring appeal is why these ancient ideas have never truly died. They have simply been translated, evolving from sacred stories told around fires into the most sophisticated equations of modern theoretical physics, all asking the same timeless question: are we living through a one-time story, or just the latest iteration of an eternal cosmic refrain? But if the universe truly is caught in an endless cycle of birth, death, and rebirth, where would we possibly look for evidence? How could the faint whisper of a previous cosmos possibly survive the unimaginable violence of a big crunch and the subsequent firestorm of a new Big Bang? The answer might be written across the entire sky, in the oldest light we can see, the cosmic microwave background. This faint, cold glow is the cooled remnant of the universe's fiery infancy, a snapshot of the cosmos when it was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. This radiation fills every cubic centimeter of space, a literal echo of creation, and it is in the subtle, tiny imperfections in this background, the temperature fluctuations that are mere millionths of a degree, that cosmologists search for clues not just about our universe's beginning, but about what may have come before. The search for these cosmic fingerprints is at the heart of Roger Penrose's conformal cyclic cosmology. If our universe is but one eon in an endless chain, and the end of the previous universe was transformed into the low entropy start of our own through conformal rescaling, then some information from that prior cosmos might have survived the transition. Penrose and his colleague Gerzardian proposed that the most dramatic events of that previous eon, the collisions of supermassive black holes, would have released titanic bursts of gravitational waves. These ripples in spacetime would have carried immense energy across the dying universe. When that universe was conformally rescaled to become our Big Bang, those gravitational waves would have been imprinted onto the new universe as slight variations in density, which later became the seeds for galaxy formation. Crucially, these imprints would not be random. The concentric ripples from a gravitational wave event would manifest in the CMB as series of perfectly circular patterns, regions of slightly lower temperature surrounded by rings of slightly higher temperature, like the quiet center of a pond after a stone has been thrown in. Finding such circles would be nothing short of revolutionary, a direct message from a time before time. It would be the ultimate evidence of recycled time, proving that our cosmos is not a one-off event but part of an eternal sequence. The implications would be staggering. It would mean that the information of the previous universe, the structure of its galaxies, the events of its history, is not completely lost but is encoded in the very fabric of our own reality, a cosmic palimpsest where the writing of a previous creation shows through beneath our own. This wouldn't just be a new chapter in cosmology, it would fundamentally change our understanding of existence, suggesting that time is not linear but circular, and that every ending is merely a prelude to a new beginning written with the same fundamental information. However, the search for these concentric circles has been fraught with controversy and immense challenge. The cosmic microwave background is an incredibly noisy signal, and extracting specific, subtle patterns from it is a Herculean task of data analysis. When Penrose and Gerzardian first announced they had found evidence of these circles in data from NASA's WMAP satellite, the cosmological community met the claim with intense skepticism. Other teams analyzing the same data argued that the apparent circles could be produced by random chance, the result of the complex statistical methods used to process the map, or from other astrophysical processes within our own universe. The Planck satellite, which provided an even higher resolution map of the CMB, was subsequently used to test the hypothesis, and most analyzers concluded that the observed patterns were consistent with the random fluctuations predicted by the standard inflationary Big Bang model, finding no statistically significant evidence for Penrose's circles. The difficulty lies in the sheer complexity of the signal. The CMB is not a pristine, clean image. It is overlain with foreground contamination from our own galaxy, dust and gas that emit their own microwave radiation, and from other galaxies. Teasing out a specific, weak pattern like concentric circles from this messy data requires sophisticated statistical techniques, and it is incredibly difficult to prove that any pattern found isn't just an artifact of the method itself. Furthermore, even if such circles were confirmed, alternative explanations within the framework of a single universe, such as certain types of sound waves in the early plasma, might be able to produce them. The quest for cycle echoes in the CMB is a perfect example of the cutting edge of science, where a breathtaking idea pushes our observational and analytical capabilities to their absolute limit, forcing us to develop ever more precise instruments and cleverer techniques to distinguish between a profound truth and a compelling illusion. Despite the current lack of consensus, the search continues, driving innovation and reminding us that the answers to the universe's deepest mysteries may be hiding in plain sight, etched in the faint, cold light that has been traveling to us since the dawn of time. Yet if the physics of loop time bends the mind, its philosophical implications threaten to unravel the very core of our human experience. For centuries, we have built our understanding of existence on the foundation of a linear timeline, a past that is fixed and unchangeable, a present where we exercise our will, and a future that is open and unwritten. This structure gives meaning to our choices, weight to our actions, and a sense of progress to our lives. But what happens to free will, to identity, to the very concept of meaning itself if time is a closed circle, endlessly repeating the same sequence of events for eternity? The idea that every joy, every tragedy, every mundane moment has already occurred an infinite number of times and will occur again forever is a concept so vast and alien that it challenges the pillars of our psychological and moral universe. This notion of eternal recurrence was most famously explored by the 19th century philosopher Friedrich Nietzsche, who presented it not as a scientific theory but as the ultimate existential test. He asked us to imagine a demon creeping into our loneliest loneliness and saying, "This life as you now live it and have lived it, you will have to live once more and innumerable times more, and there will be nothing new in it, but every pain and every joy and every thought and sigh must return to you all in the same succession and sequence." Nietzsche's question was not whether this is true, but how we would respond to the idea. Would we gnash our teeth and curse the demon, or would we respond with exultation, seeing this as the ultimate affirmation of life? For him, the goal was to live in such a way that you would welcome the endless repetition of every single moment of your existence, a concept he called amor fati, the love of one's fate. It was a call to embrace life in its totality, to live with such passion and purpose that the idea of reliving your life identically forever would be a cause for joy, not despair. But Nietzsche's thought experiment takes on a terrifying new dimension when viewed through the lens of modern cosmological theories. What if eternal recurrence is not just a metaphorical test of one's attitude toward life, but a literal, physical truth? In a truly looped universe, your choices are not truly yours. The feeling of free will is an illusion. You are an actor following a script written into the fabric of spacetime itself, performing the same lines in the same play on an infinite loop. Every decision you agonize over, every path you choose, is predetermined by the previous cycle. You will make the same mistakes, experience the same heartbreaks, and achieve the same triumphs over and over with no possibility of deviation. This presents a devastating challenge to our notion of moral responsibility. If you cannot choose otherwise, how can you be held accountable for your actions? The entire framework of ethics, built on the idea that we are autonomous agents making genuine choices, crumbles into dust. Praise and blame become meaningless in a universe where every action is a cosmic echo, forever rehearsed. This directly attacks our sense of identity and self. We construct our personal narratives from our memories and our capacity for growth and change. We are the sum of our experiences, learning from the past to build a better future. But in a looped timeline, there is no growth, only repetition. The person you are is not a unique, evolving consciousness but a fixed point in a cycle, a recording that plays and rewinds endlessly. This raises a haunting question: would each iteration of you even be aware of the cycle? If not, then from the perspective of each individual consciousness, life would feel exactly as it does now, linear and open-ended. Each cycle would be experienced as a first and only life, with no memory of the previous ones. But if awareness of the cycle were possible, the psychological burden would be unimaginable. Knowing that your suffering is predetermined and eternal could lead to the most profound nihilism, a paralysis of the will where effort and striving feel utterly pointless. Yet, perhaps there is another way to view this. If information is preserved across cycles, as theories like conformal cyclic cosmology suggest, then maybe the loop is not a perfect, identical repetition. Perhaps each cycle is a variation on a theme, with subtle differences evolving over vast eons. In this view, the universe itself could be learning, growing, and evolving through each iteration, and our lives, though part of a grand cycle, still contribute to this cosmic evolution. Our choices, while perhaps predetermined from a God's eye view outside of time, would still feel real and meaningful from within the cycle. This perspective offers a potential reconciliation, a universe that is both cyclic and meaningful, where the arrow of time within each cycle provides the necessary theater for consciousness, morality, and growth to play out, even if the entire production is part of a much larger, repeating festival. The philosophical implications of looped time force us to confront the most fundamental questions of all. What is the purpose of existence in a universe that might have no beginning, no end, and no ultimate linear narrative? The answer might be that we must create our own purpose, finding meaning not in the final outcome, but in the quality and character of each moment as it is lived, whether it is the first time or the 10,000th. The journey to unravel the deepest secrets of time is far from over. In many ways, it has just begun. While we have charted breathtaking theoretical landscapes, from cyclic cosmologies to quantum time crystals, these ideas remain, for now, largely in the realm of profound speculation. The path forward is paved with monumental challenges and thrilling open questions that will define the next century of physics. One of the most pressing theoretical hurdles is the stubborn problem of entropy. For any model proposing a recycled universe, explaining how the cosmic clock is reset, how a high entropy, dead universe transitions back to a low entropy, ordered beginning remains the grandest unsolved puzzle. Roger Penrose's conformal rescaling is a mathematical marvel, but does it correspond to physical reality? The bouncing cosmologies of loop quantum gravity avoid a true singularity, but can they demonstrably show that information and a clear arrow of time survive the bounce intact? The quest for a complete theory of quantum gravity is the key that may unlock these doors, forcing us to decide if time is a fundamental ingredient of the universe or merely an emergent illusion that arises from a more basic, timeless reality. To move from elegant equations to confirmed reality, we need more than just thought experiments. We need hard, observational evidence. This is where next-generation technology becomes our most vital tool. In the coming decades, a new era of cosmology will dawn with telescopes of unimaginable power. The James Webb Space Telescope has already begun peering back at the universe's first galaxies, but future observatories, like the planned Laser Interferometer Space Antenna, or LISA, will open an entirely new window onto the cosmos by detecting low-frequency gravitational waves. These ripples in space-time could carry the faint echoes of events from the very earliest moments after the Big Bang, or even from before it. If concentric circles or other anomalous patterns are indeed imprinted on the cosmic microwave background, missions even more sensitive than the Planck satellite will be required to find them, separating this potential signal from the foreground noise of our own galaxy with statistical certainty beyond any doubt. We are, in effect, building machines that can act as cosmic archaeologists, digging through the layers of time to look for the fossils of previous universes. Beyond gazing into deep space, we are also building laboratories that can simulate the fabric of spacetime itself. Quantum computers, though still in their infancy, hold the potential to revolutionize this field. These are not just faster calculators, they are devices that operate by the bizarre rules of quantum mechanics, the very rules that presumably govern the Planck scale where time may break down. Researchers hope to use them to run complex simulations of quantum gravity theories, to model the behavior of hypothetical closed timelike curves, and see if they truly resolve their own paradoxes, as Novikov's self-consistency principle suggests. In a controlled quantum simulation, we could, in a very limited sense, create a tiny, self-contained loop of causality and observe how information flows within it. This wouldn't be a time machine, but it would be an unprecedented test bed for the physics that could make one possible, allowing us to explore the mechanics of recycled time not in the distant cosmos, but right here on a laboratory benchtop. The potential discoveries on the horizon are nothing short of revolutionary. Imagine the moment, perhaps decades from now, when a team of astronomers confirms a statistically undeniable pattern in the CMB that points to a pre-Big Bang event. It would instantly transform our understanding of our place in the cosmos, revealing that our universe is not a one-off creation but an heir to a previous existence. Or consider the impact of a quantum computer simulation that successfully demonstrates a self-consistent time loop, providing a mathematical and experimental foundation for the possibility of time travel without paradox. Such a discovery would force a rewrite of every textbook on causality and fundamental physics. The biggest unanswered question of all, whether time had a true beginning or is eternal, might finally be within our grasp to answer. Each of these paths leads toward a future where the nature of time itself is not a philosophical mystery but a measurable, physical property of a universe that is far stranger and far more wonderful than we ever dreamed. From the relentless, one-way arrow dictated by entropy to the mind-bending possibility of cosmic cycles and quantum loops, our journey through the nature of time has taken us to the very edge of physics and beyond. We've seen how ancient intuitions of cyclical rebirth find a startling echo in Roger Penrose's conformal cyclic cosmology, where the cold, empty end of one universe becomes the hot, dense beginning of the next through a profound geometric transformation. We've ventured into the infinite froth of the eternal inflation multiverse, a reality where countless bubble universes constantly bloom into existence, each potentially operating with its own unique arrow of time, some forward, some backward, some perhaps even tied into knots. We've wrestled with the tantalizing solutions to Einstein's equations that allow for closed time-like curves, theoretical time machines where the path you take through space brings you back to your own past, challenging our most fundamental notions of cause and effect. We descended into the quantum realm, where time's symmetry at the microscopic level clashes with our macroscopic experience, and where phenomena like entanglement suggest a reality where past and future might be in a constant, negotiated dialogue. We confronted the black hole information paradox and discovered that rather than being ultimate destroyers, black holes might be cosmic librarians, preserving information on their event horizons to be potentially recycled in a future eon. We even explored how the very emergence of time might be an illusion, a holographic projection from a timeless boundary, or a consequence of our own consciousness stitching together a linear narrative from a fundamentally timeless block universe. Each of these theories, from the cosmic to the quantum, dismantles the comfortable assumption that time is a simple, linear river flowing from a definitive beginning to an inevitable end. Instead, they paint a picture of a universe where time is malleable, recyclable, and perhaps even an emergent property of a deeper, more complex reality. These ideas are more than just abstract puzzles for physicists. They challenge us to reconsider our place in the cosmos. If time is looped, what does that mean for free will, for identity, for the meaning we assign to our actions and our lives? Are we living our story for the first time, or are we participants in a narrative that has been and will be told an infinite number of times? While the science is far from settled, the mere possibility invites a profound sense of perspective. It encourages us to look up at the night sky not just as a space to be explored, but as a time to be understood, filled with the potential echoes of past cycles and the seeds of futures yet to unfold. The greatest takeaway is that our curiosity is our most valuable tool. The mysteries of time are deep and complex, but they are not beyond our reach. They are puzzles waiting to be solved by the next generation of thinkers, observers, and dreamers. Thank you for joining us on this incredible journey through the mysteries of looped universes and broken arrows. We've only scratched the surface of this fascinating topic, and the conversation is far from over. We would love to hear your thoughts. Which of these theories do you find most compelling? Does the idea of recycled time fill you with wonder or existential dread? Let us know in the comments below. If you enjoyed this deep dive into the fabric of reality, please make sure to like this video and subscribe to our channel for more explorations into the biggest mysteries of space, time, and existence. Until next time, keep looking up and